Alright, hello everyone and welcome to Handmade Hero. We are really just in a debugging situation here because I think we got everything we really wanted to get out of the lighting code. Surprisingly, just the fact that we no longer have large Z stacks in the world, we basically said we didn't really need them, so we removed them, and just that was enough to make our lighting run 60 frames a second just fine. And so really now we just have to tune it a little bit to make sure that we're casting the right number of rays now, because we can cast a lot more rays per frame than we were before. Like a lot more. Like 8 times more. Just a very, very large difference. So we'll be able to get much faster, much more accurate lighting to start with, but then we also have to fix a bunch of bugs because we are sort of, as we're taking out some of that stuff that was in there originally, we have the issue of, you know, we aren't quite right. Like as we pull stuff out, we have some certain things that are not exactly lined up the way they used to, and the old code was very highly optimized, so it's fairly brittle in that sense, right? When we do code that's kind of not that optimized, right, where we haven't like done a bunch of SIMD work and threading work and all this stuff to kind of like see when we have to do like lighting, we kind of had to see how performant it was. We didn't have the luxury of just leaving it sort of unoptimized. In that case, you end up restricting how flexible the code is or how easy it is to change, right? It's the actual premature optimization thing kind of that that Knuth was probably referring to the extent that he was, in the sense that, you know, I don't think in this case it was premature to optimize. I think we optimized it at the correct time because we needed to see what the performance was. But the point is, if we had done that just willy-nilly, you can see where you end up in a bad situation, because like it takes more work then to shift what it does because it's so tightly optimized to this one specific case. So we do have a little bit more work to do here, but that's okay. That's the nature of performance optimization. It's harder than normal code when you actually go down this route. But again, this is more what people are talking about, not the kind, like, people use the phrase premature optimization to refer to things that are in no way premature optimization. And in this case, it wasn't premature, it was at the right time, but it has those same drawbacks. Like, this is, you can see literally what is being talked about there is that it will be harder for us to modify this code because we're trying to modify code that is optimized. And that's always more difficult. In this case, we really just didn't have a choice because part of the reason we had to do this was to see how fast lighting was, because we just don't know, right? And when you have something that's this heavyweight, you really don't have the luxury of using a unoptimized version. So looking at the actual code here, if we, let me just show you where we're at. We're actually running just fine, but we have a number of things that we need to look at in terms of, there's obviously, it's a little bit buggy. So the lighting is not running properly like it was before. And we need to fix the problems with the grid alignment and how it's stepping and stuff. And that's just going to take a little while. But there's not a lot, it's not completely broken or anything. It still actually kind of looks sort of right. Like it's not that bad. So we're not far from a correct situation, but we're not, you can see there's kind of weird, there's just a lot of like what was happening there, right? It doesn't make much sense. So we definitely have things that need to get fixed. There's some weirdness going on here. And we need to sort of go through all that and clean it up. We also probably have to change a little bit about how the lighting is working. In addition to that piece of the sort of the accuracy part of the puzzle. Because one of the things that you will see in here is that the actual lighting, we want to now drive it at a much higher rate than we were driving it before. And what you can see if you look in here is that we sort of optimized this code for a very modest kind of light transport, where in each pass, we were only expecting to cast 8 total rays. And those correspond essentially to the 8 faces of the octahedral map. So we have an octahedral map that we record the lighting into. That's 8 sample directions for the lighting, meaning that in each one of those sample directions out of an octahedron, we have some resolution. Like, we can set the resolution of this octahedral map to take, more samples in the octahedron or whatever. It's just a way of representing the lighting around a sphere like we need to for light probes. You can argue whether it's good or bad or not. I'm not really a rendering guy, so I'm not going to defend it as good or bad. It's just something that works, and that's what we need, is something that works. So that's what we're using. Maybe it would be smarter to switch to something like spherical harmonics or whatever else. There's plenty of ways you could imagine storing light probe information. This one is kind of nice because it's direct and easy to understand and easy to visualize. The bad part about it is converting from specular to diffuse is expensive, and we do pay a high cost for that. So there's trade-offs in it, whatever. We're not really going to revisit that probably because it seems good enough as it is. But the point is, we kind of optimized this originally for just sending out 8 rays. Those 8 rays are 1 out of each of the octahedral faces, and then every frame we would pick sort of a new direction out of each octahedral face to trace, so that over some number of frames we would kind of like reasonably sample the sphere, right? As represented by the octahedral map. You know what I'm saying? So if you imagine that now we're going to be sending out a lot more rays potentially, then what you can see here is this is no longer probably the optimal way to do it, because what we tried to do to see what would happen if we sent out additional numbers of rays is I added this for loop here for a sample batch, and what this does is it calls the grid raycast, that routine we're just looking at. It calls that routine as many times as we want. Like, we can change this, right? And so we can slow it down to a level that's too slow, right? If I set this up to 64, so that's 64 times 8 rays per map per frame, right? You can see that I've slowed down now to a fairly slow frame rate, right? It's quite slow, right? Whereas if I drop this down to a very small number, which again is still 8 times what we were doing originally, so it's way more than the previous version, but still, you can see that we run pretty much at a nice 60. In fact, I think we can actually take a look at the specific time there. And this number here without the debug system, it's already basically at 60 frames a second, but with the debug system running, it will sometimes miss. So, in general, we could easily hit 60 frames a second with this amount of raycasting, and it's quite stable and quite responsive, as you can see, right? But even this, which is fine, we still wouldn't really want to do it this way. And the reason is because we're still duplicating a ton of work for no reason. If instead we pushed this 8 down into the grid raycast, right? So if we instead pushed it down to here, so that this simply loops over 64 things, that would be way better, because this raycast, which is this piece of code here, right? This raycast does the same amount of work in any case, no matter how many rays we send. But this, which is the thing which then computes, like, okay, what are we going to do in terms of, like, how these would get written back to the octahedral map or whatever, right? That code there doesn't really need to have its write back occur until after we've blended all the ones we're going to do for this frame. This code right here that loads the old specular map texel values, loads the new values in that we just computed, blends them together to basically do a little bit of temporal anti-aliasing, right? And then writes them back out. Right now, when we increase the sample batch size from 1 to 2 to 3 to 4 to 5 to 8 to 64 to whatever this value is, it's doing this load blend write each time. But there's no reason for it to do that, right? It doesn't have to do that for any particular reason. Instead, we could just run this code, this transfer PPS code, right? this transfer PPS code, we should put the loop there and then only do this load modify write after we've done all of the sample batches that we plan to do. And so that part is kind of the more important way of structuring the loop, and I do think we probably want to do that because there's no reason not to do it. And yeah, I mean, we really want to go fix that. Okay. So I would say let's fix that first, actually, because it's kind of an additional like weirdness in the process. And the reason that we didn't do that is originally is because the sample directions that get passed down here, this light sample directions, this part here, that part was getting prepped by this particular piece of code here that's stepping over these octahedral indices. And there's other stuff that's kind of confusing about this, which is that we don't really know what our entropy story is here. Like, you know, we have this thing where we pre-compute stepping tables that allow us to do fast raycasting, and we're basically just picking which of those tables we're going to use, and the table determines like how the ray actually gets cast and blah 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 blah, right? There's not a lot to it, but you know, that is how it's currently working. And so we want to make sure that we're actually utilizing the correct set of sample directions so that as we sort of step through, you know, we always get kind of like a reasonable distribution of rays coming from whatever sample source we're actually looking for. We want to make sure that we're actually stepping through those fairly. Like, we don't want to have some weird thing where, because we haven't really analyzed the code properly and we just kind of like, you know, smushed it together, that it turns out we're only sampling like 4 of the directions. Like, our step just always like mods them poorly or something. And, you know, those are the kind of things you can have happen when you're trying to optimize code like this and you're using table-driven stuff and you're not able to use a real random number or whatever, right? There's a lot of issues you can run into. So we probably want to make sure that we're doing that sort of thing correctly. And so we're going to have to analyze that as well. But looking through this, what you can see is when we call full cast, typically there's like this entropy index value that gets passed in. And if you look at where that actually gets worked out, it's right in here. And what I'm wondering is, you know, can we just say that maybe this entropy index just gets passed down directly? Like, maybe our grid raycast, this goes away. This outer loop here goes away, and we just literally drop it down into the other piece of code. So, you know, we get rid of this, right? And we go into this ray index code here, like this code, right? And we do something where this is going to get accumulated. So, you know, maybe it's like that. And we wrap this code up in the second for loop directly, right? So now we kind of have these 2 for loops nested the way that they should be, and so we do our raycasts 8 wide like we were doing it before, but when I say 8 wide, we're not. It's not like 8 wide SIMD. We're just doing them 8 at a time. So 8 wide is probably the wrong term. We do use SIMD, but it's wide in the collision side. So we cast a single ray replicated across 4 lanes in SIMD. We cast that against 4 boxes at a time, right? We don't do the opposite, which is another way you can write these kinds of casters, where you cast 4 rays at a time. It's called a ray bundle. You can cast 4 rays at a time against 1 box, right? So that there's a lot of different ways you can imagine doing this. One side or the other has to be wide, otherwise it won't speed up, right? So you're just trying to leverage the floating point ALU here. So if we did it this way, and we have this entropy index that comes down, right? So that, you know, that entropy index here, I'm just going to try and follow this value through to see if I can back out a reasonable way to track this entropy index across the system. You can see here it gets a sample point entropy, and it calls full cast with that entropy index. The point of this is to make sure that each one of these like voxels cells that we're producing lighting for is going to use a different arrangement of casts out of its faces, because the goal is to make sure that you don't see aliasing in the lighting based on the fact that like every grid cell casts the same direction or something, right? So it's trying to make sure that each different light probe uses a different set of directions. So pretty straightforward. So what we're going to do there, when we pass down that entropy index, it's just an index that we can use as like a random number generation kind of thing. So into fullcast we go, and you can see that the entropy index is passed in here. I don't think that this makes a whole lot of sense. I think we can probably say, look, we're going to not do it that way with the address. We shouldn't actually need that. I think I was just hacking that in before. But that shouldn't actually be necessary. So if we look at how the entropy index gets updated, this shouldn't probably be an address there. If we send down this entropy index, we should be able to do as we were doing before, where each one of these kind of gets expanded. The entropy index gets incremented in some really weird way or whatever, right? I'm not sure exactly what we would do, but you can imagine something where we just add some really weird value to it here, where we're going to step through these fairly randomly. We even could, at this point here, probably actually do a random series off of the entropy index. Presumably really wouldn't be that big of a deal, right? Now, I don't know what the best way to seed that would be, but like, you can see us doing here where we have a random series in each frame. We're probably picking, right, like you can see here, where we pick a U32 value that goes into each one of these work units. So each one of these has a different random value. And then what we really want here is to also have these to be seeded to a random value as well. Now, I don't know what we did here for doing this random seed. That's a 4x random seed, which we don't really need. But let me see. Yeah. So here's our random series PCG, which I don't know if this is what we're currently using. Looks like we have a couple different ones. PCGs aren't actually that good. I think I was kind of more into them when we first did Handmade Hero because they were supposed to be pretty good, but they're really not because they don't SIMD very well. So, it's probably not something you would actually use today, but, whatever. Times change. So when we call this, I think this random next to U32 is presumably calling this part of it. I don't actually know, but because we could take a look. In fact, I guess I can just jump over to lighting and see which one we were using. Lighting solution. Random series is which one? Oops. What is... Yeah. So it looks like there's only the H file, so there's only this one random series, and it's always an F32 4X, I guess. So that's a little weird, but I guess we always do it 4 wide, I guess. I mean, that's, I guess, how we do it. We just do it wide. So when we do random next 32, it looks like we just extract one value from it, which is fine. I mean, that doesn't really, no real issue there. But if you look at the way this works, you can see where we do a random seed here, and I guess you might say that it's a little bit squinky because I guess if we did a random seed offset, we could take a number that came from the random number generator, and this would probably be fine. So, we could imagine doing sort of a sequential update to this thing. That would be okay. Or we could imagine rolling something like this in there, right, where we are, doing this each update and going from there. I don't know. It seems like you'd probably want to keep this in scalar because we don't actually need 4 of these random values, or maybe we do. I mean, I guess the other question is, if we kept 2 of these around, could we just use those and each step through the random series? We would actually just update all 4 random numbers. And that might actually be good. So, So, that gives us an option. I guess maybe we should think about that. So if we look at what's happening inside fullcast, right, it's just the entropy does not factor into fullcast at all. It's a completely 100% non-entropic thing that's happening here. It's only grid raycast, right? where this actually happens. So if you take a look at grid raycast, this is what actually now needs the entropy, and it just needs the entropy for the thing we're talking about, which is to figure out which of the sample table, there's like this sample table, and we just want to figure out which one of the indices we're going to use, right? So we would pull out the sample direction by grabbing the table, and just we pick one of the octahedrons, and then we do all 8 samples out of the octahedron, right, at that point. So really, this part is the only part we really need. If we know that we're going to do batches, we could just use the random numbers out of the batches. So actually, it may mean that the best thing to do is to just actually use a random series and allow the random series to update each time. That's probably actually fine. I mean, maybe that's dumb. I don't know. But it kind of seems reasonable. So it could be that the right thing to do here is say, look, we're going to have a random series. That's the entropy for this. And we've got a random seed offset function, right? Like this thing. And we can just go like, okay, there's a sample point entropy, and that gets placed in here. And then we do pass down an address like we were doing before, but rather than passing an address of a simple, like, you know, rather than passing an address of like a simple index that just gets updated, we're actually going to pass a random series, and we're going to grab those values out, that actually the indices we're going to actually grab out, right? So if we wanted to do that, and also you can see how this here, you know, if you look at how this function is working, I also don't know, like, where this supposedly was going to convert itself to anything in particular. Like, you can see we've got these F32 4x states here, and these aren't really F32 values, right? They're actually just U32 values. And so I'm not actually sure, like, I'm not actually sure how we were previously planning to use these. It looks like we mostly convert them. You can kind of see here, like, how that was happening, right? Like, effectively you convert, you do a U32 to F32, right? So in this case, we would want to just literally get out the values. And if you think about what's happening here, I would assume that we don't have a large enough table set. So if you actually look at like the lighting include, there's like an INL for this, sampling spheres. If you actually look at this, you can see like how many octahedrons there are. Like, that's not very many. I don't know why it's so low, right? We probably want to increase that number in the future to something higher, I would think. But either way, if it's only going to be 16 different octahedrons, I mean, at that point, I guess my other question is, if there's only going to be 16 octahedrons, maybe we just say forget the entropy altogether. If that turns out to be sufficient, let's just do all 16. You know that like Elon Musk face where he like just smoked pot on the Joe Rogan show? You know what I'm talking about? It's like where he's got the joint or whatever. I don't actually know what he was handed. I don't remember. I think it's a joint. And he's like got like a face that's like, that face. Do you know what I'm talking about? Anybody? Well, anyway, I'm making that face right now and thinking maybe we don't care. And I would say, great. at that point, if we're always just gonna say there's only 16 octahedron, I mean, then let's just cast all 16 octahedrons. So I'm just making that judgment call because it's the easiest thing to do, and let's just find out if maybe that's fine. Because at that point, it even removes one more step to this process, which is to say that now we just don't need entropy at all. So the entropy is just gone from the system, and the sampling is just literally over the octahedron. So we basically have this U32 octahedron index. It's just going to be 0, and then it's going to go to whatever the octahedron count is, and that's like it, right? So then we don't use the mask or any of those things. We just say like, okay, the sample direction is going to be whatever the, whatever the computed offset is into the table. And that's it, right? That would be it. So I have to think about if I'm missing something here. There's also this other thing, light sampling sphere mask, which, again, don't really remember much about that. I think that's probably going to be below these here, right? Yeah. So there's a sphere count of sample directions. And it's using the same offset. I really couldn't say I know why we have both of these. Sample direction table. Like, what is the point of that? Hold on a second. So the sample sphere doesn't get used. So those must have just been old things, I guess. So that just goes away, right? So in here, we're just grabbing the octahedron that we're going to use, and that sample dir we just pull out of here like it's this, right? And this function doesn't get past sample directions, nor does it get past... I mean, we could pass it the base pointer if we wanted to, but nor does it get past the... what the heck is quadrant index? So, quadrant index is just which of the four... Yeah, okay, that's fine. We don't care about that either. So that can still stay in there. So if I get rid of sample directions, I just want to see where we're at here. So does this guy not have the solution pointer? No, he does. So he has that. We have the octahedron index, sample directions, array index, walk table offset. So this is it's just these. I mean, that's all it is. Right. And so the only thing is, what is it complaining about? Sample batch did not get replaced. So this would do all of them, right? This would do the entire set every frame. And the only problem is this code right here. Where transfer PPS gets written to the RGB for this particular array. You know what I'm saying? You can see here that I'm grumpy about this. Apparently, like, this part didn't really get optimized. That's okay, because we're now sort of changing a little bit how it works, so maybe we want that anyway. So we'll find out. Yeah, we can probably update this to be better than it is, right? Because we can fix the way that it actually gets sort of handled through this loop when we're doing kind of final optimization. We don't have to do that now, but we can make this better for sure. So when we look at this, really what we're talking about now is if we just clear this instead. So here, where we start at transfer PPS, this used to not bother clearing it because it wasn't actually gonna ever get used. It was always gonna get overwritten. If we now clear it first, and then we go ahead and do basically a sum where we average all of the things together that we put in here, you can then imagine this to just being a plus equals, right? This sort of a thing. And we should be able to multiply this by the weight, like, like ray weight or something. And you can see that this is just stupid code. Like, this should be done wide and isn't. You can see why we put this comment in here. So that comment remains true. This should all be done wide, and then we just convert it down at the end. But at the moment, we don't care too much about that. But if we just do an accumulator there, right, so that we accumulate those values together, just average the samples that are sent out, we know what the ray weight is. It's just going to be how many octahedrons we're going to do. So it's this value here. So if we just take the total number of octahedrons and we say we're going to do all the octahedrons that we have, that we generate, we are going to divide that, 1 over that number. We're going to divide to find out how much each individual octahedron should compute to the whole. So we have 16, so each one contributes 1/16 of the lighting answer, right? And we do that each time. We now get rid of any sort of external understanding of like what the sample directions are or what the entropy index is or any of that stuff. And now we're literally just stepping through the rows of the atlas table as we go, right? Now, I guess to be honest, I'm not sure I understand how we know which one. So, like, I have to think about this. But SY here, like the Lighting Atlas text cell, like which one that we're using, that I don't understand how we know. So this is a little confusing. So let's try to work this out, because this, I don't remember how this works, and there's a little bit of an issue here that I'm not sure I follow. So when we like call into grid raycast, right, we've got the spec texel here, and the spec texel is what the first texel is in the row. You can see that we're going to step by y's and write all the x's. When we pick out a sample direction, I don't think I understand how does this know which row we're on. So this seems like either there was a bug in it already. There's 3 possibilities. There was a bug in it already. A, seems probably unlikely. B, I don't really understand what this code is doing, and I missed something. Or C, I accidentally deleted something very important. So, here's what I'm trying to say. We go over these ray indices here, and there's 8 of them. That's not an accident. The reason there are 8 is because each row of an octahedral map, because we said that they were 8 by 8, each row of our octahedral map, there's 8 rows represented here by the SY loop. This is the 8 rows of the octahedral map, right? And these 8 rows of the, I think, by the way, we did this already. The 8 rows of the octahedral map here are then, this 8 is the 8 columns of that row of the octahedral map. Now, each one of those has to go out a particular direction, right? So the sample direction ray index, this part here, is what makes sure that you're grabbing the correct one. But what I don't understand is how did this walking of the indices has to be correct for the direction, which at this point I don't know that it is. It's probably not. That might have been the bug. So when we look at the sampling spheres part, I don't understand how this got packed in here exactly, right? You can see there's a total light sample direction count for these sampling directions. These are the directions that come out the sphere, right? And you can see here that we've got this, which is light sample directions per octahedron, this is what I'm talking about. It's a square, right? It's the map dim, which is 8, times the map dim, which is 8, right? It's 8 times 8. So the total number is the octahedral count times the light sample directions per octahedron. You know what I'm saying? I think you know what I'm saying. So I think the part that I'm missing is these are packed. These are obviously packed so that we have them in the correct order, right? We've got them in the order where it is by row, then by column, or whatever, right? And so this has to actually respect that, and right now it would not be. You know what I'm saying? So light sample directions per octahedron, this is actually not correct. Yeah. So this needs an SY value. So I guess what I would say is we really just need the base pointer in here to be something along the following lines, right? If you imagine the sample direction is just unpacked here, right? Then we actually would know what the sample direction offset is. So the light sample direction here for sample dir, we can actually compute that index directly. It's going to be the ray index is the minor index, so it just goes each time, right? It's the octahedron index times the light samples directions per octahedron, right? Then it's going to be plus the row index. So, right, and this ray index is really column index, right? So the row index times the light octahedral map dim plus the ray index. That's the actual, like, that's the actual way that this is being stepped. You know what I'm saying? And since this piece of code doesn't actually know the actual SY, it can't compute the correct value here, and that was the one missing piece that was confusing me. But it's not confusing me now because I worked through it, right? So what we actually want to do here is, you know, honestly, we really would rather rebuild the lighting table to go in the correct order. Meaning, what you'd rather do is just make it so that right, take a look at how this is stepped. This is the thing that's actually in the outside loop. So what we would rather do is move this as the prime index and the octahedron as the interior index, so that we inside here just step it one at a time. We don't have to do that right now, but that's just smarter at that point, right? It's a much easier for the code to be understood. So I want to do that eventually. Okay. So let's assume that we go with that. Either way, we do need the SY value here. And maybe that gets rolled in here too. I don't know. That's a good question. But if we take a look at how the SY value works out, so in fullcast, all it's doing is stepping through those texels and calling grid raycast, right? That's like the only thing that it actually does. So it may make sense to now actually finally collapse these routines so that grid raycast gets welded in here, right? As this gets simplified, we may find that that's possible. I don't know. It may or may not be. We're gonna, we'll have to see. For the time being, though, in order to keep things relatively straightforward, what I'm going to do is slightly simpler than that. I'm just going to pass the SY value down the line. So in here, there's just going to be like a SY value that gets passed in, and I'll just put, so after the work value, that SY value will get passed down. And so if we have the SY value, then we can back out the sample direction value directly here, and we can just say like, okay, here's the sample direction table, here's the octahedral index that we're talking about, and we just need an additional value in here for, I don't remember what the value was. Where's that INO? It is this. So we take the base pointer, that's the entire table, we offset it by which row we're on, right? As well as which octahedron we're on. And right now it looks kind of like that. You know what I'm saying? So as you step through the SYs, this is what you get, right? And I don't actually remember, I want to check to make sure the SY value isn't offset there. I don't know, it might be, no, it's not, right? So it's stepping from 0 to 8. So that's fine. Total casts initiated is now totally false. So now this is going to actually include this number. So that's fine. But doesn't really matter at the moment. Okay. So when we call full cast, we have the tile, the center, and the entropy index. So the entropy now goes away. And, we can leave the sample point entropy in the work order just in case we decide to add it back in. There's no real cost to having it there, but if it turns out that all this stuff works to our satisfaction later, we can just pull the entropy index out entirely because now there's no actual entropy in the lighting system anymore, which, maybe is good, maybe is bad. I'm not actually sure which one it is. Okay, so now we're actually also totally stable. Like the lighting has none of the artifacts anymore, which suggests that that was a bug. It is, however, set at too low of a blend rate right now because the blending's now happening automatically. So what we should be able to find somewhere in here is like an over 60, the actual value here. This should be able to crank this up to something much more aggressive. So let's say it only takes maybe 4 frames for the lighting to be completely up to date. So a low amount of lag, right? Which would look like this. And, it looks okay, but you can see we get, there is a little bit of shifting that's happening. Oddly enough, it seems to happen mostly when the lighting slides. So I assume that has to do with the fact that we have some weird artifacts there. Like I don't know, that this is probably because these are no longer centered. As you know, we kind of have them now at the corners of these things, which is not what we intended originally. So there's a little bit of that going on as well. So we're getting closer now, but we still have this every time the lighting shifts. It looks like there's like kind of weird artifacts based on your alignment. Where you are, because when you're stationary, even if the light moves, it's kind of okay, but you can see, it doesn't look quite right. So I think we probably still have some bugs in how we're indexing these things at the very least, right? And we can sort of go from there. That said, again, pretty stable. I don't know what this value should actually be. I think let's hold off on tuning anything like this until we actually do a debugging pass, which I think is what we want to do now. Looking at the performance of this now, we're not even in the fullest performance build, and I think we're pretty much okay. It's not quite as good as I would like it to be at the moment, but it's not bad. And now we're in a very stable zone, I would say, right? We're in a very stable zone for performance. So I think we just concentrate on getting this now to be less buggy, but I think it will be pretty stable going forward. Also, we can, if we want to, we can add some more. We can figure out some ways to maybe add the entropy back in by generating more light spheres, and every frame we use a different light sphere set. We didn't do that originally because we already were thinking that we wouldn't do all 16. Like, 16 was the number that we thought was the total amount we'd cycle through, and we did one every frame. So it took 16 frames to sample all the octahedrons. Now we're like, okay, that was fine. Like, we easily can do all of those. So maybe we want to up that number, right, to 256 spheres or something. And then that way, we can still introduce some entropy to the system. That's why I said I didn't want to pull that out later, because we may find that we actually still need that. Okay, but at the moment, we're fine for performance and stability, I think. And now I think we're just in bug land, and we want to go figure out how to reduce the sort of bugginess of the actual light computation, which I think is probably wrong. You know what I mean? I think it's, since we made the simplifications, I think it's probably incorrect at the moment. And what we're going to want to do is, sort of reduce the sort of wonkiness there by actually going through and looking at where arrays are being cast from, make sure they're being cast from the correct place and that they're stepping properly, all that stuff, because we kind of shifted that stuff a little bit. And we do have a bunch of like debug code in here, right? So that we can look at individual light casts and things like this. And do various stepping. So when we debugged the lighting the first time around, we left in the code that we would need to be able to fix some of that stuff. And so, I think that is, we shouldn't be starting completely from scratch. Like, we've got stuff here that we can use. You know what I mean? All right, so let's first just make sure we're all on the same page here, because like I said, it's been a while since we looked at this code. So we now step over all 16 octahedrons that we have. We grab out the sample direction batch by saying it's the table times which octahedron we think we're on times whichever row we want. That gives us our initial sample direction. And then we're going to go over all 8 of those sample directions one at a time. We're going to produce after the raycast and doing like sort of the computation of the reflectance and all that stuff, sampling. This is basically where we sample the old octahedral map, right? When we do the sampling, we figure out how much we're going to transfer, and then we sum that into our transfer value. We are going to do that for every octahedron, so we're going to do that 16 times, and then we're going to write it out once to the final map, right? So that's what this is doing. And this right here applies that blend rate. So that t-update blend rate, that's what this is, right? So we're going to do that, and we do that for anybody who is not inside, who doesn't start off inside one of our grid leaves. And we sort of determine that's actually kind of buggy, though, because if you're enclosed by a light, you are not supposed to be completely dim. Like, you should probably have at least whatever the value of that light is should be what you write in as your light value. Like, you should be radiating that in all directions, right? Because you're basically like enclosed by the light. So I don't know how we want to handle that. I don't know what we want to do. It could be that the correct thing to do there is something else, but we probably need to do something about that. So that's going to have to change, and we know that's going to have to change. That said, everything else I think is fairly straightforward. I don't know. There are a few things that might not be true anymore as well. So one of the things that we did here is we computed the walk table, and we verified that it's faster to compute the walk table and just look up the walk table than it is to produce the walk table dynamically on the fly. However, right? However, we don't actually know that that's true anymore now that we've moved to 2D. Because this was for 3D, which is a lot more complicated because you have 3 possible step directions you can take, X, Y, and Z. And 3, when you're talking about a really tight loop, where everything counts, 3 is a lot more expensive than 2. 2 is literally just one branch, right? Either you're going to go a step in Y or you're going to go a step in X. When you have to do like X or Y or Z, you can see how maybe that would have tipped the balance in favor of a table, whereas if you just have X and Y and it's just a straight Bresenham walk along there, not only might it change, but we could probably do a literal like integer Bresenham walk or something like this, where we don't even use the float, where we don't even use the SSE registers, right? So it could be that we could actually hide the cost of doing the walk, which would get us out of the business of building these tables at all, right? We could literally do the comparison, just the one comparison each time, and go. Now, it may be that that is still just too expensive because it's mispredicted, and having a table that just you always grab whatever it is each time is just too compelling, right? I just don't know. I just don't know. So we probably will have to run that test again at some point. I don't think we should do it now, but, at some point that is something we would probably have to figure out because we definitely have, we definitely have some flexibility there that we didn't have before. So, all right. If we take a look at how we do the get quadrant 4 stuff, let's just go over this one more time. Because again, this is subtle as well. So the way this works is we're going to loop over all of the sample directions. You can see how this works here. We're going to loop over all the sample directions, and the sample directions are for whichever, whatever particular node you are. We have this idea that the actual places you're casting from they're finer grained. Like there are more light nodes. In fact, I think we can just put that back in here. I'm going to turn on draw octahedral values so you can see what I'm talking about. So these are the locations. If you can see there, these are the locations where we are actually taking light probes. So each one of these places stores a light probe value. And on each frame, we cast out from these. So on each frame, we cast however many rays it was now. So it's 16 times 8, so, right? I think? No. It's 16 times 8 times 8. So it's 16 times 20, so 16 times 64, right? So we cast 16 times 64 rays out of each one of these every frame, just to let you know how powerful computers are, right? I mean, yes, we completely multi-threaded this, and yes, it is SIMD, so it's utilizing the performance of the CPU well, but, I mean, come on, man. Computers are fast. So we're doing those casts out of each one of these, right? But the thing is, if you look, and I don't know if we have enough debug space for these, I should probably switch to using the other debug diagram stuff, but yeah, we don't. So where is our debug lines? Debug line count. Let's just give ourselves a little more debug space here. All right, what? Oh, is this just because we have we only have 16-bit for line indices? So the problem here is actually just that, like, we can't actually fit this many lines. Yeah, we should just fix that. We should just have multiple line batches, because that's the problem that we're getting here, right? Is that we end up with too many of these when we push them on. So, we could fix that, right? In fact, it should be pretty easy to fix it, right? Let's just see what happens if we try to fix that here. So if we go to when we do the draw debug lines, the lighting values when they actually push out the debug lines there, right? This. I feel like this is actually a lot. I don't know why we didn't do this before, but I feel like we could just solve this by breaking this up into chunks, right? So if we did something like this, which is like debug lines left, and we just said, all right, this is how many debug lines there are. If we want to keep the indices always below 16 bits, because that's what we have for dispatching to the graphics card, and we don't want to bump that to 32, it seems pretty easy at this point to just say, well, whatever the debug lines are left, we'll just say, as long as there are debug lines left to draw, we will compute a batch value, which is just whatever the minimum value is between how many lines are left and what fits in 16 bits, right? That kind of thing. We'll then just like go through those, and maybe we can do this with an offset so it'll be a little easier for us. We could do something like this. So we say like debug line index, we'll start at 0, and we'll just say, look, while the debug line index is less than however many debug lines there are, we will compute the value of the lines left by subtracting where we're at from the total number, like so. And then we'll just say, look, we're going to do as many as we can, which sometimes is all of them, and sometimes is only 16 bits worth. We'll then ask that for that value. We'll loop through that value. And we will have a subindex here where we push, we push the line segments one at a time. Like so. When we're done, we just advance debug line index, by the batch count, and that should allow us to just batch these up into 16-bit capable chunks, which in theory should mean that we don't have a limitation, right? Or at least I think it should. We should probably switch this into... Hold on a second. Yeah, so we should probably switch to the debug mode to make sure this is actually going to do it, because it looks like it still doesn't like that, but I'm not sure why it wouldn't. Do we have a total frame limit on 16 bits? Do we never reduce those? Do we never rebase those values? That would be kind of weird if that's true, but it might be. Here's where we like update batches. It sure looks like this would be fine, right? So if we take a look at what this says here, there's a max quads per batch that already has this baked in, right? So it looks like this should work, meaning it looks like as long as we, don't try to call this value with something that's too large there, it sure seems like that would work. I mean, it could be the fact that this is slightly off. I guess the problem is the max quads per batch value. We probably need this to respect. I mean, you just, like, here. Let's suppose we just said the max batch value is 4,000 of these, right? Yeah. So we just need that batch value to be, maybe we need to export that from the renderer so that we know, like, look, you have to provide a number that's sufficient. But anyway, now we're out of the we don't have the issue anymore of having too many debug lines. We can have as many as we want, so we can draw everything. Now, of course, there is the issue of we can't figure out what the heck anything is, so there's that. But if we turn off like maybe rendering the occluders, we can look at the sort of thing that I was talking about before. So if we go, and in fact, you can also kind of see here in this area where you've got the occluders drawn, right? Or I should say where you've got arbitrary stuff drawn. So just things are being drawn that are lights or occluders. You can see that, for example, we have trees in this area, right? That's what these all are. But then you've also got like this stuff, which I don't have any idea what that is. I assume those are the lights right there, wherever the lights are. And you can also see kind of the problem that I was saying before is that like plenty of sample points are inside where the lights are. And right now we're treating that as if they're inside occluders, but they're not. They're inside lights, right? So that's an issue. To be sure. So, So I'm not sure what we want to do with that. We're going to have to think about that a little bit more, right? Inside here, you can see there's a lot more occluders. That's because there are ceiling tiles. So those are the ceiling tiles there. And those are there just because interior spaces need to have bounce from the ceiling. Exterior spaces obviously wouldn't have bounce from anything. But interior spaces, even though we're not drawing a ceiling, want to have lighting bounce from the ceiling. So that's why those are there. Similarly, you can see the thing that I was talking about before where, you can see how these bits are kind of off. So the first thing I think I might want to do is let's try to restore the alignment of these to actually be aligned more on the actual, like, I feel like these want to be aligned so that their centers are at we want the centers of the sampling to be at the centers of our actual grid because that's where people are going to be most of the time. So we'd like to have the lighting computed properly around like where the things are we're actually lighting. And furthermore, it avoids problems of like having stuff that's right on the boundary of being inside or outside something, which again is just creating a lot of problems for us that we wouldn't ordinarily have to deal with if we're not putting our probes right on the boundary of where something goes from being inside to being outside, although we probably do need to deal with that in separate ways, in other ways anyway. But so why did we get that alignment change? Last weekend we basically had that happen, and I'm assuming that it has to do with the fact that I'm assuming that when we went to change the alignment of things in the world to not use Z, we used the +5 offset. Like we used that offset by a percentage of a tile, right? And so if we want the lighting to be centered around it, the lighting center would also have to be offset by that, right? So when we do our alignment in the lighting code, we need the lighting itself to align to a tile boundary that's off by that same percent, that same fifth of a tile. Like so in here, right, where we do all this stuff like voxel dim is one fundamental unit and blah, 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 right? And we do all this stuff to determine like where the thing is going to be, which is right down here. And we say, all right, it's going to be at this particular offset. Right, you can see here where we're saying like we set the offset to this particular value and all that stuff. So this part needs to be offset by that 0.5 of a cell dim. Right? So I mean, really, I think I don't know to what extent this is going to be exactly correct, but I think we're really just talking about like Atlas min corner, the X value would be offset by whatever the voxel size is, right? So half of one of these voxels. So the, like, when we pass in here, we've got the voxel dim, right? I think we just want this offset by half because that's how things are aligned in the world currently. Something like this, right? And we should be able to do, I don't know if we've got XY, but maybe we do. Yeah. So if we just offset the XY by that much, leave the Z where it is because that's this kind of absolute thing and it's offset differently, then in theory, the location where we take these samples would now be centered. Whoa. That's some interesting light poisoning. Presumably because now it's sampling off the edge. That's pretty cool, though. You have to admit. That's some interesting light poisoning. But anyway, light poisoning aside, I assume we effectively want to do that, right? Like, I assume we effectively want to sample lighting at an offset of the boundary like that. Now, why that would actually produce the light poisoning that we just saw, though, I'm not sure why. So, you know we've got some bugs in here, so it could just be related to other problems that we're having. It might not really have anything to do with that, and this just exposed it. But the fact that that occurred was not what I was expecting. So that's a little disconcerting, right? I don't understand exactly why that would have provoked it, because in theory, this should just be... In theory, that sampling shouldn't really have much to do with anything. And the alignment relative, the alignment of the cells of the spatial partition should be the same either way, because the whole thing got shifted in that direction. You know what I mean? So you can see that, like, the cells of the spatial partition also got shifted 0.5. So there really shouldn't have been a behavioral difference. I don't know why this, in particular, like, leaving this out, I don't know why small changes in that alignment should produce light poisoning like that or not. I can't intuit that. offhand. So that's really confusing and a bit troubling. I mean, it may just be that, when we go fix whatever other bugs we have, that just goes away because it's actually just a product of one of the other things that we haven't sort of debugged yet. But if it does actually have to do with how they're aligned, I don't quite understand why that would be. So that's a bit weird, right? I don't understand why that would be, because the spatial grid is derived from the Atlas grid, so these two are always going to be aligned, so the lighting system, in theory, the part that I'm not intuiting as to why this would make a difference is it shouldn't really matter like where I slide the lighting alignment. If I move it just a little bit in one direction, why would that change the like feedback properties of it, right? It doesn't really make good sense to me. It's possible that it's totally fine and it's just related to something else. Like, we know the lighting is busted, and we have to debug it. So it could be that that's just an artifact of the bustedness. But I don't know. It's a bit confusing, to say the least. So anyway, I'm going to leave that in there for now because I think the more bugs we have, the better in this case, because the sort of more obvious the failure of the lighting, the hopefully easier it will be to find those bugs. I love that light leaking over time. It looks super cool. Unfortunately, we would rather have that happen when we want it to happen and not when we don't. But, what are you going to do? Anyway, so let's nerf that out now. And let's start talking about how we want to look at these values a little bit more closely. So, so I guess I would start with the observation that there is very clearly... That's just really strange. So I think we're just sampling directions wrong. I mean, honestly, I think that's mostly what's happening. You can see that here it's like, oh, everybody seems to suddenly be able to see the light source in one case and nobody can see it in the other, and that strikes me as just a sampling issue. So I feel like we probably just have a sample direction issue here, where we're not really sampling the sample directions the way that we think we are. And so I think what I'll start with is, now that we can, I'm going to go back to debug draw octahedral values, and I'm going to put back in the thing that draws the actual octahedral map so that we can see those. And now that I know that I can crank my debug line count up a bunch, I should be fine to see them all, right? So what I'd like to do now is just, these are our little kind of I don't know if those of you remember those little koosh balls, right? They were like, you remember these things? They were all the rage for a little while, in the early 90s, maybe. I want to say, maybe. So the koosh ball is effectively what we're drawing here, right? We're drawing a little koosh ball. And the koosh ball shows us what the lighting is in any particular direction from one of these light probes. So it gives us a way of sort of trying to figure out what the heck is going on, because it's hard with lighting It's easy to debug an individual raycast or something, which is something we're going to want to do for sure, because we may find that our raycast is just busted or something like that, right? So we can start small. It's easy to debug an individual raycast, but then it starts to get kind of harder when you talk about just like, okay, is the light transport sensible right now or not, or various things like this. So if we take a look at the little koosh ball, it kind of helps us a little to figure out what's going on. And we can sort of see in certain cases, I think I would like to turn on the voxel cells. So draw spatial grid. I'm going to say, like, let's draw part of the spatial grid and not the other part. So this is just like me going, you know what? Don't draw the actual, like, occluders and stuff. I don't want to see those. Let's just draw the cell boundaries, just so I can see where they are. So here are like the cells. They're drawn inset slightly, only slightly. So they, there's not actually a gap between them, but they're just drawn that way so you can see them a little more clearly. And if you look, you can kind of see like some nonsensical stuff here, right? You can see that these particular koosh balls got basically no lighting, even though these got tons of lighting. So there's some fairly nonsensical things going on. And what we determined for these sort of blatant ones here, and in fact, I guess I can turn this on temporarily so you can see it, although it just becomes too much, unfortunately, to really parse. Hopefully you can see it if I narrate it. What you can see here is that actually these are inside lights. So you see how there's a light that moves with the hero's head here, right? And you know what? You can see a pretty obvious bug there too. Like, why does that not update now? Like, what's going on? So there's some pretty weird stuff happening, right? You can see how strange this is. So, I mean, it's kind of good news, right? I mean, it's never good news that you have a bug, but it's always good news if the bug is blatant, because it gives us a better chance of finding it, right? Lighting can be real. Like, you see what happened there? Those were black as I hopped through them, which is what you would expect to have happen with that if it's enclosed, right? Like, you can see it's entirely enclosed there. But that one that's now entirely enclosed, yeah, that one does not think so. It thinks it's still outside, right? So you can see that this is really blatant, which makes me think that actually our raycast originator is just broken, which would make perfect sense because we butchered it, right, in order to go down to this new 2D sort of flat plane version that we're doing. And so I think we just want to start there and work our way up from the raycast, because I think the raycast might just plain be broken. That's my guess. Because it does make sense that these things inside the light are registering as black, because we do have code that does that. It does not make sense why they're not registering as black consistently. So that is wrong. You know what I mean? So the hero's light box, sometimes red and sometimes green. The reason for that is just to make it easier to see which node it's in. I mean, easier to see, and this is kind of a laughable thing to say because there's too many boxes. But what's happening there is just that if you look at the spatial partition, I colored it so that there's cyan and magenta alternating, right? And so when you turn off, like, let's turn off the non-occluders. So the actual spatial grid will now go away. And this is just the occluders. What I did is I colored the occluders based on which cells they were in, just so you can see alternating cell boundaries. So as the hero's light source moves between cell boundaries, it will be cyan when it's inside a cyan boundary, like in that case, or it will be magenta when it's inside a magenta boundary. And when it moves between the two, you can actually see that it will be clipped. So half will be magenta and half will be cyan because it's in two different nodes at once. And in fact, if we do, I think we have a thing here. I don't even remember where it is. in like a time. There's like a way to slow the time step down. So if I really slow the time step down, so that I can hop the hero like really slowly, you can actually see what I'm talking about here. So like, you see how there's like 2 boxes? You know what I'm saying? So basically, the coloration here doesn't show any state information. It's purely just telling you what node things got sorted into. And currently, like, to the best of my visual ability, given that this isn't the world's best visualization, but to the extent that I can parse it, it sure looks fine. Like, the spatial partition looks correct. I don't see any obvious indication that the spatial partition is wrong. Maybe I'll slow this down a little bit here. So as you move things, such as the hero's light source, around the spatial partition, even when the spatial partition is sliding, like it is now, or doing things, it looks pretty much right. Like I don't see any evidence that things are getting sorted wrong, or that boxes aren't clipping properly into the spatial partition, or any of that stuff. It all actually looks like A-okay, right? So it looks to me like the place to start is the raycaster. The raycaster looks like we probably broke it. And that makes perfect sense because it was pretty crazily optimized. Like, because that was the part we were just trying to figure out how fast we could make it run. It makes sense, right? Heroine wants to suggest something. In line 152, should the first factor be sy times 16 times 8? Do you mean this one right here? By the way? This one. Okay. I don't believe so. But again, we haven't really looked at this closely. So just to explain where that number comes from. So when we compute the lighting table, we have this thing called light sample directions per octahedron, which is 64. Right? So I don't think so. Because this is already the number it should be, right? Like, it's 64. You know what I'm saying? I don't know where you got 16 times 8 from. So if you really think it should be 16 times 8, then that's not what it is. It's actually 8 times 8 at the moment, right? But assuming that you meant 8 times 8, that is what that factor is. It's baked into here. I don't know if that answers the question. But like I said, this stuff we need to go look at. So this may be wrong. I don't think what you're talking about is wrong. But then again, like I said, this kind of needs to now be updated because we really kind of changed dramatically what it was doing. And so this was highly optimized for the case that we had because we needed to take some performance analysis of it. So we didn't really have a choice. And now we're kind of changing some of those assumptions. So something, it could very well be wrong. I'm just saying why I don't think what you were saying is wrong based on my current analysis of how this is working, but that is far from final, right? Does that make sense? Yeah, it's a bit weird because there's a loop outside here over 8 things, and a loop inside here over 8 things. And what's actually happening is the stride here is getting picked up by this. And this part might be wrong. Right here. Let me think about that. No, I think that's right. So basically what you're doing, right, is you're saying, here's the sample direction table. It was built basically wrong because it was built for the old way we were looping over these. But we don't really want to go change that right now. I mean, we could, but, we didn't. So we're still using the same lookup. And the old lookup used to be you would loop over all the SYs and all the SXs. So it was an SY SX loop for one octahedron, which is 64 things. What we're doing now is taking one octahedron, which is 64 things, going into a random row of it based on what the outside loop tells us to do, and then going over 8 of those. So we're effectively like doing 8 and then skipping 64 minus 8. Like we're going 64 forward after having done 8 in that location, going 64 forward and doing 8 there. Does that make sense? And the reason we're doing that is because the table was made for the table was made for octahedral index being the outer index, SY being the middle index, and SX being the interior index, and we flipped SY and octahedron. Now we're doing all the octahedrons for one SY, right? So if we built the table now, and like I said, when we went over this code, I actually said this, and I mean it, we should rebuild the table to actually be in the other order, where SY and SX octahedral index are sorted so that we go SY first, then octahedron, then SX. That's the actual order we want, right? Because we update rows of the map at a time, and then inside the rows of the map, we want to cast lots of rays for each column. And we weren't set up to do that before. Hopefully that explains a little bit. Does it? About how this is working? Yeah, it's non-intuitive specifically because the table was built for the old way of doing it, and we are trying to not update the table right now. But this is not how you want it to look. You want it to look the way you were just saying. So the reason that they don't match up is very specifically because of that weirdness, right? So anyway, unfortunately, I think this is probably still correct though, right? I would like it to be wrong because then it would just be like something that maybe would cause the problem. But I don't actually think it's wrong right now, but hold that thought because again, we have not really done a good pass over this to make sure that that's true. So it still could just be wrong. I just gave you the explanation of why I think it's right at the moment, but that could just be complete BS. And when we actually look a little bit closer, we'll find that, in fact, actually no. Right? All right. So getting back to the raycast itself, I think what we want to do now is try to actually get some kind of verification that the raycast is working at all. Because it's entirely possible that when we change the computation of the walk table, let's say, that we just completely broke it. Like, it could be that the raycasting is just not working anymore. One of the problems with something like lighting is it's really hard to see errors. Like, when we're looking at it, we can see that it's probably not right, but it's just such a subtle, like, lighting is such a subtle thing that although we can tell it's probably not perfect, we can't tell how it's broken. We just kind of see that it doesn't quite look right, but it's like your brain doesn't have a lot of intuition when it looks at something like lighting unless it's just completely bonkers, where you just get complete nonsense, and your brain's like, oh, like there's nans in there or something, right? You know what I mean? When you get to this point where you're like, well, it's probably not working, but it kind of still does look like lighting, the problem we have is you're just, nothing's going to jump out at you, right? Like, you're not going to look at something and go like, oh, it's probably X, right? So what we need to do now is kind of go into a more detailed analysis of like maybe some test cases, like pick some isolated particular places to cast rays from and see what the raycast result does, because we probably just have some fundamental bug in like the raycast, right? Where we're actually just, stepping through the grid wrong so that rays are fairly arbitrary and incoherent or something like this. We probably have something going on like that. And so if we have something going on like that, that helps us understand what the heck, it will help us understand what the heck is going on by isolating some cases. What I would like to do at the moment is ask the question, what the heck is going on in here, right? So this part, I mean, you can see some oddity. You can see some oddity here. This code, when we do full cast, is basically saying, all right, find out if you are inside, if one of these lighting nodes is inside a leaf of the spatial partition. And it looks like what we do in that case is actually not to write black into it, but to actually write nothing into it. And so that means that the thing that I saw when I was like hopping along and I was like, oh, that seems wrong. Actually, the thing that was wrong is the thing I thought was right. Meaning when we hopped over something and it did change to black, that actually is the thing that doesn't make sense. Because according to this, we don't update those values. They just stay the same. So I think the first thing I might suggest is if we look at how this code works in the SY iterator for writing these texels, I might add something here that at the moment will just be for debug, but eventually we'll want to actually do something here, where we loop over these spec texels, and you can see here us like doing a read modify write on the spec texels. What I want to do here is to just say maybe we are going to just write like black. So here, you know, eventually we will, or you know what, we could even do something fancier than that. We could write magenta, right? Let me take a look at our SIMD code here. I assume we have something for loads yet. So let's do a magenta thing, right? If we wanted to write out magenta to each of these slots, it's a little bit squinky the way that works, because we're writing out 4 times 6, 24, right? We're writing out 24, but it's actually 3 times 8. So it's first color goes here, second color spans these two, right? Makes sense? Then we're back here. And that's one pack, right? So it's color A, you know, color 0, color 1, color 2, color 3 for a pack of 4. And then it just repeats again, so I can actually just use the same pattern. But this will just cold write magenta directly into these slots. For the spec texel, and that will let us see what we actually think is interior and what we don't. So when we run this, right, here is our purple, magic purple set. And what you can see here is actually that's just totally correct. So that piece of code is definitely working right. Right? So that thing we saw where it was going to black before was like another bug, right? That's like another buggy thing that's happening there. I also, the weird like strobing effect that you see there, that should really not be occurring. So that also feels like our copy is busted. Like we've got a lot of broken stuff, right? So I think this is actually not that bad. It just means that when we did this sort of like adjustment, we definitely broke stuff just like we thought we would. And hopefully as we work through it and remove those bugs, that'll be the end of it, right? It'll be correct. So you can kind of see what's happening here. This looks like we kind of had a bug in general that we didn't know about originally in our lighting code, though. We never really thought about the fact that lights would fall into that region. And so you can see here, those are the sources of light. They were actually getting set to black, which is totally wrong. Before. I mean, they wouldn't be set to black, but they would not be picking up light from their actual local light source like they should have been. So we actually kind of found a bug there that we never really addressed in the original version as well. So this will actually be better in that way too, because we'll come up with a solution for that, like allowing casting, allowing it to do a gather when it's inside in some way, or another, right? And Clan Sweeney, I totally agree with that comment. All right. So this is good, and I think I might leave this in here for now. We can turn it on and off at will, so, maybe while we're debugging some of the other things in the lighting, we can set this to off if we want to. We can also sort of have it set to on, but have a choice of what happens here. So we can do like a something more like this. Where we just clear everything, so everything is going to go to black now, which will probably be more useful for debugging the lighting so it's not leading to magenta bleed into everything. So if we clamp the black values to black now, and we can probably turn off the spatial partition because maybe we'll turn it on again from time to time, but we can more or less turn off that rendering because at the moment it looks totally right. It appears to be where's our octahedral value? Oh, I'm in the wrong piece of code. There we go. It looks like the spatial partition is always creating the correct actual partition. We are just looking up into it incorrectly or something like that, right? So I don't think we need to draw that at the moment, as far as I can tell either. So looking now at this, we should be able to now start focusing on, like exactly what you expect. And you can see, like, just looking at the koosh ball display, you can see, like, some pretty obvious indications that things are wrong here. Like, it doesn't really make a lot of sense what we're seeing in these koosh balls anyway. I mean, you wouldn't, like, why is there an equivalent amount of light coming from the left of this and the right of this when pretty clearly more light sources are over here on this side, right? That doesn't really make a lot of sense. There's no light coming from over here that we know of. And we similarly, like, we have no idea what's producing this weird green light out here, right? Probably something to do with out of bounds fetching incorrectly or something. So, we've got issues, right? And like I said, that's not really a bad thing because the more pronounced they are, the easier they're going to be for us to know if we found them. So all right. So moving on, looking at the koosh, I want to take a look at this at the quadrant stuff, and I want to think about what we're actually seeing quadrant-wise. So we've got this thing that does a quadrant index, right? We look up into the lighting walk table, and I don't actually know where we actually compute that, or I should say allocate that. In here, we grab, the sample direction table. We have the sample direction table from the INL file. It's this thing, and it's going to be that the light sample directions per octahedron, right? This whole thing. You know what I mean? So we have the sample direction table, and we index into that based on where we are, which direction we're heading out of the cell. And then interior to that, we have the quadrants, right? So when we do compute walk table, we pick these XY quadrants. They used to be octants, now they're quadrants. Because the resolution of the spatial grid is half that of the actual sampling of lighting, because we just found that we weren't having enough occluders in there, right? Um, uh, yes, Greg, Greg Inc. That's exactly right. Another way to say it would be the more blatant an error is, the easier it is to find. And so the worst thing is if you have like a really subtle error, one that is causing perception, like you can see that the lighting is not quite as good as you think it should be, but it's like you really can't find any obvious reasons why. Like it's not like, oh, there's blatant, here's this obviously grotesque error, right? Because it really doesn't give you any idea where to look. You know what I mean? Um, you the more like pronounced an error is, the happier you usually are, and the more subtle or rare an error is, the scarier it is, because you're like, the harder it is to see this thing occur, the less likely I am going to be able to find it, right? Like it just keeps getting harder and harder to track, the less of a trail it leaves, right? Now, the bad news is we probably also have subtle errors in the lighting, because you almost always do. So these ones that we're looking at now are going to be the easy ones to find, and then after they're gone, the bad news is there's probably also subtle ones. So it's not quite the same as saying, yay, we only have, blatant errors. It's more like, I'm happy to be working on the blatant errors now because I more or less know we're going to have not so blatant ones later, and those are going to be bad, right? If that makes some sense. Hopefully that clarifies that a little bit, right? Subtle errors are the worst by far. By far. I mean, they're so bad that sometimes you don't even know you have them, right? That's the real thing. If an error doesn't appear to you, like you don't even know it's there, that's the worst kind, because then it crops up later on like a end user's machine or something, right? So it's like, right? So usually you really, really hope that your bugs are bad, like they have bad obvious effects that occur on your machine and in a reliable way, because you have a really good chance of finding those in a reasonable amount of time. And the opposite is not true. Like the subtle bugs, where you can't really tell, is the lighting, it kind of feels like it's a little wrong, that kind of stuff, that's just the worst. Because, then you're really talking about having to be extraordinarily meticulous, and you have to add all of this infrastructure to try and like, okay, can we, corroborate these values with some other system? And, it becomes really difficult. So you usually are very happy in something like lighting anyway, usually very happy if something's obviously wrong. That's like a way better situation than when you're just got that sinking feeling. It's like, it doesn't feel like it's quite right. A lot harder. Anyway, so when we do our walk table computations here with the remainder stuff, I want to see if those are getting computed properly in the grid raycast, or if I at least think they are, right? I want to just do a quick check to see how those are actually getting computed. So, like, the remainder is getting pushed down by fullcast, I think. Yeah. So basically what happens is the outer code that calls fullcast, that code is stepping through the voxel for sampling. And at each point in the voxel for sampling, we know that we're in whatever quadrant is like the truncation of Atlas index, the like anding of the bottom bit, if you will. So like X is like 0 quadrant, 1 quadrant, 0 quadrant, 1 quadrant of X, and Y is like 0 quadrant, 1 quadrant, 0 quadrant as we step through. So when we do this Atlas index, when we pass the Atlas index in here, we divide it by 2 to know where we would be in the spatial partition. And we are basically using the remainder to know what the quadrant is that we're in. Now, the problem with that is that we should verify that it still works out to be the correct partition. This Atlas to spatial grid index offset, that presumably is like 110 or whatever, right? Let's find out if that's actually true. Yeah. So it skips one spatial grid because there's an apron in the spatial partition that basically says, like, if you're inside this apron, you're outside of where we're sampling lighting, so just stop your search, right? So that offset prevents you from being in the apron, and the other part here, this half Atlas index, is the part that says where you actually are inside it. Drawing this seems good. Like, if we should probably draw the raycast to make sure that it's picking the correct spatial index. So we'll have to test that out in a second. But anyway, so then when we loop through here and we look to see whether we're in things, I feel like the initial grid index computation, so this computation, kind of has to be correct, because if it wasn't correct, this code wouldn't work. And we kind of verified that it did. Like, if you look at where the blacked out koosh balls are, they're exactly correct. Like, I don't see any error there at all, period, right? I do see errors in shifting, so like that when we slide, that just looks totally wrong. That should not be happening, right? So our copy, like when the lighting, so that slide does not work properly. So we definitely have to debug the slide, and that's fine. That's just the block copy operation. But the actual spatial partition lookup appears completely correct. Like, I don't see any indication of it being wrong. So I think we can safely eliminate this particular part where we compute the initial grid index. That seems to be correct. Now, is the quadrant index computed correctly? I suppose it could be wrong. But we at least know that the initial index isn't wrong. So maybe the quadrant index could be wrong. I don't know. We'll have to see. But this part seems correct. All right. So looking into grid raycast and compute walk table. These have to agree because basically compute walk table is just pre-computing what gridcast would have done had we figured out which steps to take directly rather than building a table for them. So when we look at how the table is laid out, I'll be completely honest, I'm not really sure exactly how this is working, so I may want to go look at walk table entry here. I guess, well, okay, so I guess I see what's happening. But yeah, so this is a little bit squirrely. So you can kind of see how this is packed in here. We've got the lighting table, and for each of the entries into the lighting table, we are storing 4 different tables, one for each quadrant, which makes perfect sense, right? That's fine. But and you can see too here, like, you can see why it would make sense for us to be able to compute this on the fly, which we might now be able to do. I'm not sure how much it would cost we did the analysis before when it was octants and in 3D, but it might be different now that it's quadrants in 2D. You can see why this is annoying, because when we actually look at what the quadrants are, it limits our ability to change the spatial partition's relative size to the sampling. If it's computed on the fly, we don't have that problem. If it's pre-computed, we do have that problem. Because pre-computation involves storing a table. The more offsets you can be at inside the spatial partition, the more tables we have to store. You know what I'm saying? So I do think computing this on the fly would be better if we can now get away with it, which it's possible that we would be able to, because it would just be a very simple, we could do a very simple Bresenham that just does XY, right? So it only has to do, like, it would be branchless, and it's fairly simple. And maybe the Skylake can figure it out okay. We really don't know. So anyway, I feel like we should probably try that. I just don't want to do that yet because with so many bugs in play, we don't want to be changing yet another thing. So I want to first get that working with the table and then swap it to dynamic. Also, that way we can see if we take a bad speed hit for switching it to dynamic. Or maybe we could even get a speed improvement now. Who knows how that cost has switched. So in here, what we're effectively doing is saying, well, there's going to be a quadrant offset, which we compute by just looping over the 4 quadrants that there would be. And the starting location puts sort of a cell dimension, it puts us a quarter of a cell dimension in to start with, and then it goes a half cell dimension from there. That seems like that would always be correct. And again, we don't care about Z anymore, so we're just only talking about X and Y. So it seems like that would always be proper. Yeah? That seems correct to me. I don't know, maybe it's not. But anyway, we go through the sample directions here, we pull them out, and we do the walk. We do an overcomplicated thing here because it used to do all 3 dimensions, so you can see it kind of doing more probably than it needs to. Really in this case. And then, you can see we had some debug cases in here we were doing before. They're still here. We pretty much just do what you would expect, and we choose which one of these we want based on whichever the best dimension was, at the time. This is the delta. This is like where how you'd step through it, right? And I don't really see... I don't see anything particularly suspicious in here. Yeah, I can't say I see anything suspicious. Like, that just all looks pretty reasonable, right? Um, there's nothing particularly... So one thing that's a little odd is, so the way that T-terminate works here, not actually sure I understand. I guess that just prevents us from casting rays particularly far, right? I don't actually know. In grid raycast, I assume we just don't go further than that. You can see here, like, whenever we end, we just do... And, you know, this is interesting. So when we get to a terminator, like if we cast outside, you can see here us doing the, like, sample out of there. That may also be part of the reason we get that light leaking. We'll have to think about that, whether this is actually what you want or not. But either way, so that T terminates just there so that we do gathers. If, you know, things that are far away, we don't just keep casting forever. We do gathers on those. So I guess I would say, like, I don't see any obvious places in the code where it's wrong. So I think the thing we want to do now is go in there and try to draw one particular raycast. I don't know what the best way to pick a raycast direction would be. But, you know, at startup, I would say, you know, this seems kind of implausible anyway, probably. You know, I think we could probably just do at startup, we could do a cast, and we'll pick one that happens to be close to the hero or something, and just look at what it looks like, because most of the area seems wrong. Like, most of the lighting seems sort of subtly wrong, at least. So probably we can go from there. Let's make sure before I start this that the walk table stuff actually does make sense. When you look at the light sampling walk table, and you look up the quadrant index there, I wanted to see, like, in the lighting solution itself, how exactly was this? Yeah, so this here, the light sampling walk table here, has an index value of 8. It doesn't need to do that anymore, right? It's only 4 now. But other than that, I mean, that was just extra space that's not being used. Other than that, it's fine. It's exactly, you know, it's used exactly the same way, just the top 4 entries aren't used. So, you know, it doesn't actually need to be there. And the way this is getting indexed is exactly how we would expect. It looks up the quadrant index. It offsets it by whatever the walk table offset thinks it should be at that point to produce the, for this particular ray direction. And then it just uses that walk table entry from then on. And that seems correct. So it's like we left in some of this test code here as well, too, for like things like checking boundaries. So that's kind of good. It's not turned on right now, but that does let us do some further testing. So you can see here like the very simple update that we're doing as well. All seems normal. I guess I don't quite see how T-terminate is working here. Why is T-terminate written differently per step? Does that make any sense? That seems a little weird. Like, why do we need to update T-terminate per step? Like, wouldn't you just... I guess we're just doing that as a convenience feature so that you just look that up in the table so you don't have to pull it yourself. So when you get to a terminate, like when cost metric drops below 0, you just use whatever that termination position was and off you go, I guess. How does cost metric get updated? Interesting. So we actually had our cost metric. Our cost metric is just weighted by how many leaves you tested. What an interesting dynamic condition. I don't know if that was really smart or really weird, but I like it. So that value might be a bit low as well. Right? Like, that's a really kind of conservative value. Like, only 8 squares of testing. And I can see why we may have done that before because we were trying to optimize things, but that may also just be kind of not necessary, right? So I don't know what we want to do about that. I don't know how flexible we are here. Like if we wanted to do more than that number. How would we feel about it? Like, it still seems pretty stable in terms of frame rate, so I don't think that cost was too particularly bad, right? Like it's worse, right? You can see it's definitely worse. It's more like a 30 frames per second, but it's also drawing a bunch of debug stuff. You know what I mean? We need a way of we probably should have a thing where we do an actual test that doesn't have to do, that doesn't need debug stuff in it, right? But yeah, so that value could stand to be a lot higher, and I suspect we probably want it to be a lot more like 16 now that the lighting is pretty fast, because I feel like it wasn't much light transport before. If it's only doing 8, I don't know. It's hard to say though. It's good to know. Like, I'm glad we know that number is there and that we can change it to something else, because we'll see. But at the moment, I guess I would say, who knows. So I'm gonna put a to do in there because, let's tune this value in the future. Maybe it should be more than 8. Because that's pretty conservative. That's basically saying you're only going to search through 8 cells. And if any of those 8 cells were like complicated and had like 2 or 3 leaves, then it's even less. Like maybe it's more like 5 cells that you're going to search through. And since the gather is kind of bucket brigade, like it's still going to sample from where the ray ends. It's not like the lighting doesn't still transport over distances, but it transports more slowly, right? On the other hand, it does reduce the error that's introduced in casting rays particularly far, because they start being they're not very dense in terms of how they're sampled. So it is hard to say what this correct value should be. Maybe having it low is actually good. It could also be that we want to stop doing a cost analysis and just do a distance. There's a lot of ways we want to think about this. So I would say that we'll, want to talk about that a little bit more. So that's going to need a little more work, for sure. For sure. Okay. So let's try to get more sane here. Let's try to get a little bit more in the weeds. So when we actually do our raycast, we have a bunch of things that help us draw what actually happens during the raycast. So I think what we need to do is kind of re-enable those, right? When we pass down the debugging thing here, you can see us kind of doing some debug drawing, right? Here's us showing like what we were looking at and what we were testing against, right? So, yeah, I guess we just probably want that to be turned back on, and I would say we probably want this to be like a pound define. So that I don't have to like go through all of these conditions manually and turn them on and off. So we probably just want to say, like, look, if we're debugging, oh, I forgot about this H comp. We do someday need to figure out whether that H comp is a good idea. At the moment, nobody knows, right? Got a lot of little like notes about probable bugs in here. Maybe our bugs are in some of those routines. All right. Now we don't really know which one of these we want to debug, but it shouldn't be that hard for us to figure out. You know what I mean? We have some kind of a complaint here with rect center dim. Looks like there's... Is rect center dim... It's 2 V3s. Is probe sample p single maybe not the right kind of value? Yeah, so the problem is probe samples. We updated this code now. Probe sample p single is really ray origin packed, comes in directly. It looks like, um, that puts ray origin single in there. So I wonder if maybe that value needs to be replaced with ray origin single. I'm not sure what it actually wants to do. So it's taking probe sample p single, ray origin single. It's really just that probe sample p single. So the probe sample p single looks like it's never really single anymore. Like, we probably just didn't update the name, right? But it's always computed packed now. And you can kind of see, like, this does the entire sample. You know, we compute the coordinates off of this thing. Although, to be honest, I don't totally understand what this is trying to do. Like, this is wide, but it's always still just a scalar value. Like, you could extract any given one of these and it would work, right? Yeah. So I don't know. My assumption here is that we can just extract this. Like, we can just do, like, any component of probe p single is what we want to draw here. I think. We'll find out, right? Although I guess we can't. It's not a get component because they're packed in like X, Y, Z. So, no. I guess we need to do this. Make sense? So we just need to turn them into sort of the scalar version for use with the debug routines, and I think that's mostly what we're talking about here. And this is like, you know, actually E012. Well, they might be. I don't really remember how these worked out. Yeah, no, it's E. So that's kind of a pain, but, you know, whatever. It's just a piece of debug code, so we don't really care. So with debugging turned on, we should now be able to send down a request to debug something in the grid raycast here. It's a little difficult to figure out how we're going to handle this because we're doing 8 rays at a time. So which one of these is going to be the one that you debug is a little bit confusing. But presumably it just does the first ray in the set. I guess we could try to make something that allows you to select a subray out of that, but at the moment we'll just do the first one. Problem is, it could be that the first one is correct and other ones are wrong because we're stepping through this table incorrectly. So we probably will need to do something where we pick a particular one, right? So like in here, we turn on debugging based on which one of this, like what the actual octahedral sample versus, and ray sample, we do one particular one of those to pluck out a particular value. So, like that might be a little bit of an issue for sure. But we'll see. So inside fullcast here, what we want to be able to do is send down a debug value here, like debug true at some point. And I guess because we know what the atlas index is, like, I think this code is probably what we want, more or less. It's just kind of old, right? So if we put this in here, it's really atlas index X, atlas index Y, and atlas index Z, and they want to all equal something, like whichever the debug value is that we're looking for, right? So it's like, oh, it's, it's some particular one of these, who knows what. And then debug this gets sent down as, in this grid raycast here or whatever. It looks like this one, I'm not sure why these two are separate. Maybe this was not one we actually care about at the moment. It's really this one that we care about, right? So like that. Then when this gets called here, we just need to update the SY here. Will just be, let's say 0, because that's the debug. That's the SY we're going to debug. The rest of this looks a little off. So the initial grid index and then the quadrant index. So basically like this, because we changed this around, looks like that. And this will allow us to do a debug pass on whatever we set solution debug grid index to be, right? So in here, debug grid index is currently set to some random thing, right? And debug ray index, I don't know where that gets used by anybody. I guess that's what tries to determine which one of these we're going to do. Yeah. So these are done internal right now. So that's kind of a problem because, so although this value we can pull out the correct thing for TY, TX is handled internal now. So that's not going to cut it, right? Now we could pass these values down, which maybe is what we want to do. Like instead of debug, there's like an actual debug like packet that you pass down. That has this information in it. I don't know. So yeah, I think we may have to kind of like update the way we do this a little. Maybe we make a little debug bundle that has like exactly what you're trying to debug. You pass that down and you go from there. Okay. So I think this maybe is not so useful. I'm going to get rid of this because I don't think we care about that anymore. Yeah. So this should draw a raycast, I believe. And we'll see. But I believe it will draw one raycast. But we have to actually pick which one we want it to be because we have no idea which of these raycasts it's actually going to draw. And maybe I will like turn off some of this other debugging now just so I can see it a little bit better. Because we actually also don't know like where it is at the moment. So maybe I'll turn off the octahedral values. And we'll see if we can find out where that's going to be. Also, we probably should try to set it. Maybe that there aren't that many of those in the world. That we may have it set to a value that we never actually get to because we reduced the number dramatically when we got rid of the Z slices. So probably the actual debug, this is probably too high. In fact, yeah, it's 24 by 16 by 2. So like, if we look at how many of these there actually are, let me just launch speed crunch there. 24 by 16 by 2 is 768, and this is set to 717, right? So it's like gonna be like one of the last things off in the corner, like up here or something like that. So, you know, it may even be like in an apron or something. So let's try setting this down a little bit, and then let's try like, you know, I don't know, whatever this is going to be. And we'll set debug ray index to 0 or something, and we'll kind of go from there. All right. So I don't see it though. So let's step through the code and see. We may just never. We may have a bug where we're not actually triggering that code path, right? So let's go ahead and take a look at that. Actually, also, the other thing I would say is we probably want that grid debug grid lighting thing to control the outer code as well. So we, you know, in the code where we did if grid raycast debugging, that probably wants to be like a pound define that's up at the top of the code, or maybe like in here or something, to control this, because we want that grid raycast debugging control to also happen uniformly, so that the calling code enables, right? Like this code here wants to enable at the same time. That's my story, and I'm sticking to it. So then, when this code sort of does its thing, we should at least see this stuff running. So it's a bit weird that we don't, and I don't really know why that would be. So let's go ahead and set it to debug mode and find out like why we don't ever seem to actually get any stepping. Like why are we not seeing those little steps in there? And I don't know. So in the lighting code here, let's make sure this is running correctly. So here's the debug build doing whatever the debug build is doing. And then if I go down to that code inside fullcast, which is right here, you know, does this ever run? So solution debug grid index is 200. Initial grid index here, like, just is never 200. Is that what we're learning? That sure seems to be the case. So when we did the light lookup voxel dim, am I misunderstanding what the actual dimensions are that we step over? And if so, that's a pretty bad mistake on my part, because that means I don't understand how the actual light propagation code, like, it should be stepping over those total values, right? Like, what's the deal? So let's take a look at Atlas Index. So these numbers we would expect to range however voxeldim is ranged, which is exactly what I looked up, right? I mean, the number that I did was 24 times 16 times 2, right? Oh, nope, I'm wrong. So actually, grid index is the spatial partition, and the spatial partition is only half that. So the spatial partition is actually 12 times 8 times 1. So there's hardly anything in the spatial partition. There's hardly much of a spatial partition at all, right? Which is weird. Again, sort of suggests that as we've collapsed this down to 2D, I mean, there could be situations where there's lots of things involved, but it's starting to feel like maybe for this raycasting you want much coarser than we're using because now we're not using Z and blah, blah, blah. So, you know, we'll cross that bridge when we come to it. But, so all right, that's fine. Debug, oops. Debug grid index. Let's try something much more conservative, like 30. And now we are finally in the debug code, thankfully. So that's good news, and yeah, it's just good news. So now we should be able to see it. I mean, hopefully. I don't know if that's actually true. But we also might want to run it in O2. Because debug builds are not fast enough for lighting at the moment. Everything else is fast enough, but not that. So now we just want to figure out if we can see it. It looks like it's now like hey, there's the debug, right? Where it's doing some casting. And you know, if I had to say, I would say that's pretty wrong. Like, exactly what I think is happening seems to be happening, which is that this code is kind of busted. So, let's try to move this into position. I think we actually have a weird way of doing that, that we put in here that's kind of ridiculous. Like, right, there was like this thing. So we can actually move it to like something that's inbounds, like that. And we can see where the actual hit location is. I will say that hit location is correct, right? Like, it actually did the raycast downward, and it properly picked the floor, right? So hey, the good news is our debug visualization is quite good, actually, so we're still in a good position there. I'll be honest, I don't actually remember what the purple line is. We have to go look at like what that's supposed to be. I have no idea. But let's go ahead and re-enable this, because this is not really going to work properly now, this purple line, because it's like we're not properly tracking like which ray we're trying to cast. So we should probably try to make this be an actual, thing we pass down for debugging. And to do that, I'm going to need like debug ray pick, something like that. And in debug ray pick, I am going to have to pass down like the particular index, I guess, of which ray you want. Although yeah, I don't know. We'll say that there's an enabled, and then in here there's going to be something like a pick value, and I'm not sure. Maybe we do it like this. Like, I don't know. where you can basically say which ray out of the 8 ray pack and which octahedron out of the 16 octahedrons that get cast, like, which one are you talking about? It's something. I don't know. So if we imagined doing something like that, then when we go to do grid raycast, then actually the debug value here is like this. Something like that. Debugging in this case equals debug pick enabled, right? Something like this. Although, also I don't really know why these are separate. That doesn't really make a lot of sense. They probably should be together. This probably wants to be done slightly differently. It probably wants to be done like that. And then debugging is actually deferred to here, where we actually compute this value as something based off of the debug pick per ray. So in here we would say it's if it's enabled and the octahedron index is correct and the ray index is correct, well then you can have your debugging. And in any other case, you can't. So debug pick octahedron index. You can see I'm just peeling these off one at a time. Debug pick ray index. And that way now you can sort of slice that off and just, you can say exactly what you wanted to have happen on each individual raycast. In the case of here, we don't want any debugging, so we can just pass the garbage value. I think I might keep it as a default parameter here, though, because we probably want it to only happen when grid raycast is happening in the first place. So we may want to do something like this, because we don't actually want to pass a value here at all. If we're not, that doesn't actually need to be there, right? So then we have this debug ray pick bundle, and we'll pass that along. And in here, we're just going to say, enabled is obviously true. Octahedral index equals something, and ray index equals something, right? So we can now pick out which specific one we want, but we have sort of this whole situation is probably less than ideal. I'm assuming what we would actually want here is just to have the solution actually pick out each of these things. And maybe we can clamp each one of these, right? In a way as well. I'm out of water here, which is not great. So we may want to take a quick break and get some water. That probably should happen. But whatevs. So I pretty much just need to make this so that we can pick these more easily. And if we do so we could probably just change the debug pick to maybe just be a pass-through. So like maybe the grid index is in here as well. It just gets ignored inside the raycast team, but otherwise it's fine. And all of these are like debug pick dot, So that's like debug pick dot grid index, right? Debug pick this, that, the other thing. That seems like it makes some sense to me, maybe. And then the TY value would be one more thing on here, right? So there's like the grid index, the SY, the octahedron, and the ray. And each one of those you could sort of adjust separately to like pick out each individual piece of the problem that you have, right? So let's go ahead and implement that, but I would say let's take a quick break and get some water, maybe even a snack. Is everyone cool with that? Maybe? Anyone? Bueller? Snack time? Yes. Everyone says yes. What? Insobot. Oh my god. No, Insobot. No. Wrong. All right. So snack time. Take 5, everybody. Take 5 and do a snack time, and we'll be right back. No, I'm not providing the snacks. What do you think this is, Google? We don't have $12 billion of snacks for all of our... Like, no. You got to provide your own snacks. All right. Hopefully everyone has snacked up. Everyone have their snacks? Breakfast of Champions, honeycomb cereal. I think we can all agree. They tried to change the formula for honeycomb cereal, and it was awful. And everyone complained so much they changed it back. And I was like, thank God. Because honeycomb cereal is great, but the new one they tried to change it to was terrible. Absolutely terrible. All right. Let's do this. So, yes, choose the Force. I still inhale it as an adult. That's what I'm saying. All right. So, we want to be able to set these up here. And now we kind of don't really need to have this be constructed here. We can probably just pass this down directly. So we can sort of do something where we check the grid index here. And then we, assuming the grid index passes, we just pass the solution debug pick down directly, like so. And this quadrant index value, though, that's a little harder because we need to be able to compute that, right? So we probably want to make sure that it's the same, like it should be the same quadrant index that whatever we computed, because we're checking to see we're on a particular one. We should use the same quadrant index, right? So I think that's okay. And a lot of these values we don't care about, right? These are not relevant anymore. So, like none of this stuff matters at all. Like at all. Expected direction is kind of nice. We probably want to keep that. And we still can, because we will know the TX and TY. It's basically this, and maybe we want to call it that. So we have TX and TY here, like so. Maybe that's just a better idea. And that way we can pull those values out as necessary. So I don't think we need like any of this. That's just gone. But this we do want. So we want to do our debug pick tx and our debug pick ty. That seems good. And similarly, like that would get, would be that. We would pull it out of that, and off we go. So I think that's all good. We just have to make sure that we now actually track those values. So instead of this stuff, like these two things, we now have a debug ray pick like this. And then in the places where we were allowing you to edit those before, we need like actual thing to allow you to pick them differently, right? So I don't know what this is complaining about. Initial grid index around. Is there no grid index in that? I thought we put a grid index in there, right? Yeah, we did. What's the problem? Oh, it's not a real 32. Okay, well that's fine. We can fix that in a second. That's going to be TX now. Okay. So I think we're all good. Now we just need to make sure that all this stuff is reasonable. So we don't really know what we want all this stuff to be, because we don't know what ones we want to actually debug. But that's a question for the next thing we're going to do. So we should here be able to do like, okay, solution debug pick enabled equals true. Or maybe it's this raycast debugging, like it's enabled if we set that to 1. I don't know what to do about this part here. I guess we just say, hey, we want to be able to do each of these values separately. So there's the grid index, the octahedron index, the tx, and the ty. And we want to do each of them, so have fun. Right? All right. So I guess the first thing we can say is we already know that like something's wrong about this. Like I screwed something up, right? And it could just be the debug stuff because we put it in there, but we noticed this right off the bat when we first did it. So my understanding is that the ray direction, which is that yellow line there, it does seem like the ray direction is sort of working in some sense, meaning it's going, and it's doing some kind of an actual raycast there. And if we go into the lighting control panel here and we move the grid index around, right, which I guess we don't have we should probably, that's why I said our debug system sucks. That's one of the first things I said was like, we have to improve the debug system someday. If we change this value to something over here, which I don't remember what it roughly was, we'll have to have something that allows you to pick U32s easier. But if we make it something further over there, I mean, it doesn't even matter. You can even just see the error here. You can see that it's the expected direction, which I believe is this that line that's magenta. It's not going in the direction that we actually raycast, right? So that may just be because we tweaked the debug code, but it could also be like, hey, that's problem number 1. Like we're casting in a different direction than we think we should be casting based on the octahedral map's output direction, right? So first things first, those two things have to line up, and they ain't. If we go to full cast, you can see where those are getting drawn. So this, right here, this is saying, for the specular atlas, we have a debug pick TX and a debug pick TY, right? We have to check to make sure that those don't include the apron. They might. Let's double check. It looks like those kind of include the apron. Sort of. Like there's a -1 in there. Right? So that seems maybe like this is actually this. Like we actually want to add one because this includes the apron. That's my story and I'm sticking to it. However, doesn't really help because they're still wrong. You know what I'm saying? So the direction we expect for the XY that we're writing to is not the direction that is actually getting cast. And so that's like, I mean, problem number 1. And you can see us drawing the expected direction here from the location that we start. We're drawing out the expected direction. That's the purple line. And then when we do our grid raycast here, which presumably is slightly wrong, when we are drawing this stuff, where we, do these debug boxes and push like sort of the ray as it goes, you can see probably at the bottom here, we do like a long ray, that's how far we go, right? This whole thing is just wrong, apparently. Right? This value, where we pick something out of the sample table, and we, get the direction of it, that direction does not necessarily match this. Now, I guess when I think about it, that's okay, because this is a direction straight out of... So it doesn't have to be exactly right. I guess so false alarm. As long as it appears to come out the same face of the octahedron, it's fine. Right? I guess is how we would put that. So that's actually okay, I guess, now that I think about it. That's all right. All right, so the next thing we need to do is make it so that we can edit those U32 values, right, in some way. And I think our trick for that before was to say, we just make them real 32s because those were editable. I'm not sure how I feel about that, but, it's probably the wrong time to go monkeying around in here. Although we really would like to improve this debug stuff because it's terrible, right? It was high on the list of things to rip up entirely. But, so where we have editable F32s, we, at the moment, don't have any way to actually edit those. That is an interesting debug UI. I don't know what that's supposed to be. There's like literally nothing in it. Okay. I guess we don't put anything in that file anymore. So where we actually edit these in the debug system here, which is, like I said, way too complicated for what it does. So simplifying this is high on the list of things to do. But when we actually draw these out, we've got sort of a thing for editing these, where if it happens to be an F32, we have a way to edit that, but if it's not, we don't, right? And so, when we draw these, we track whether you can hit them. And when we do that, there's the interact left code here, which I forget exactly where it is, but here it is. You can see like Booleans can toggle, R32s can drag, but you know U32s can't do anything at the moment. So you can see here, if we wanted to, we could have a pretty difficult to edit because it's not very good, but you could see having a U32 one, and excuse me, it would just be that. So maybe we allow that to occur. I don't know. Or maybe it's just terrible. I guess we'll find out. So not sure why I can't. There we go. So I don't actually know how we want to deal with dmouse p here because I'm not sure if that's like normalized. I'm not sure what we keep those coordinates in. But mostly we probably just want this. We probably just want like a sign or 0, which I guess we don't have. We only have sign of, which is a little unfortunate, right? So I don't know about that, but presumably we just want something more like this. If it's less than 0, we would ink. If it's greater than 0, sorry, I mean deck. We would ink, and if it's equal to 0, we just don't do anything. You know what I mean? And that'll give us crappy editing of those values. Right, so, you know, it's not good, but it's workable for the immediate moment. So then if we kind of look at what's happening here with these casts, I guess I can't quite say what I'm looking at there. You can see there's kind of some weirdness here where you see like multiple cast values. I don't really know why, right? And, you know, we're going to have to clamp these values because at the moment, if you go outside of the 16, you would get a kind of meaningless value. But what's interesting is it seems like it's doing kind of weird things where it's like casting straight down for some like large number of these. So I don't know, like I do want to go like get this working because it looks like there is some badness going on here. So let me just add a clamp for these and then we'll kind of walk through them and see like why is it doing what it's doing because I don't really know. So inside the lighting code, where we put those debug values in, when I go through the grid index thing, I guess when we do equals grid index or whatever it is, oops. What just happened? Debug pick dot grid. There we go. Search woes. When we actually get this, we want to clamp these values, I think. I don't think we have any real way to clamp stuff that's, you know, I think these are all just for floating point most of the time, so I don't know. No, it looks like we do have some S32 stuff in here. So we should probably be able to do some clamping here. And what we would want to do is make sure that, like, all of the values that have fixed upper and lower bounds are within those upper and lower bounds, right? So we know that like the debug pick TX value can only be between 0 and 7. And the same with the TY value. So those have to be clamped. We also know that the octahedral index is only allowed to go up to whatever that predefined constant is in the generation table. So like you're not allowed to go over whatever the light sampling octahedron count is. So that is the maximum value it can take. And so we'll just make sure that those values are clamped so that if you try to do something higher than those, it just gets thrown out. Because otherwise we could crash, like because the debug, although this part wouldn't matter, it just wouldn't pick anything because you'd be out of range of any value that it actually tries. Same with the grid index, right? That's not true for TY, because TY is actually going to say where in the table you're going to look up. You know what I mean? So, you know, it does matter. All right. So if we have it all, if we look at like some of these things, maybe we put them right in the middle there, right? The first thing I would say is I don't totally understand what I'm seeing. Like, I don't really quite get why I'm seeing multiples. I think what I'm seeing here is that it casts 2 Z layers. Because, which I guess makes sense. So we're seeing 2 different Z layers because the grid index in the spatial partition will be the same no matter which one you are. And so it may make sense for us to change that to an atlas index, and maybe I'll do that right now so that we're only picking one and not many. That, to me, seems saner. So while we're at it, let's make sure we can pick explicitly one of these. So we have a atlas index here, not a grid index. So when we're looking through this, we have an atlas index. I don't know if we have an R equals comparator for those. If we do, it would just be this code, and we do. So when we're setting this up, we would, actually set it to something. I don't know what. 8, 4, 0, or 1. I don't know. Doesn't matter. And so that way we can actually see these values. I don't know if this is possible to edit. I don't think it is. So I don't think we want to pass it down as a single debug value, right? Because we don't have an edit for that. So what we really want is just the X, Y, and Z separate. And we can clamp those as well because we do know the dimensions of this, the sampling grid, right? So when we are going through those, we should be able to clamp those as well. So where we do our clamp of each of these, we can also do our clamp of atlas index. So we need the voxel dimension for the actual, we need the voxel dimension for the atlas grid, right? And so the voxel grid here, we want the cell count out of that voxel grid. So we would want like atlas grid cell count X. We want to clamp it. Now, I don't know if we have a clamp that works with V3s. One of the bummers about this jump stuff that's in Forcoder Flurry is it doesn't show you any of the types. So when you look at clamp, you have no idea like which clamp is which, right? It doesn't really have overloading where it just tells you the name of the thing. So I don't actually know if we have one because, like I said, on Handmade Hero, I program on it so infrequently that I don't remember like which stuff we've written and which stuff we haven't. So I have no idea. But presumably we cannot do this. Like, I assume we don't have the ability to do that, where it would just do the whole clamp for us. I'm not sure, but let's find out. Yeah, it looks like we don't have one. But we could just add one. It seems like the kind of thing we might want. So if we just had a clamp function in here that we appended, right? So in math, maybe, if we just had a clamp where we clamp each individual member, that seems like something we would use. Maybe it's not. I don't know. But it seems like something we would use. So let's suppose we just add that to this set of things we've got here. Because you can see we have quite a few things that operate on these like integer, 3-wide integer vectors, right? So maybe we just add a clamp. The clamp would be something like this. And I don't know if we have minimums or maximums for vectors, and I guess I don't care. I probably will just do it like this, where we say clamp min x, vx, max x, and we just do exactly what you would expect. Oops. So now we should be able to do this. The only problem is this is an actual maximum value, not a dim, so this also needs to have 1 subtracted from it in order to be proper. Other than that, I think it's fine. And then we should be able to like actually pick exactly who we're looking at. So I don't remember. Oops, that's debug break, which is not what I meant to do. I don't remember. I had to learn which command this is. Okay, so it looks like F7 is our friend for lighting. And so in theory, I don't actually know if this is true, but in theory, we should be able to edit these. Although I can't. I'm not sure why. Oh, is because it's an S32? That's an interesting one. So I guess technically you would just do that, and you would allow drag value to happen. On both. So I think that's fine. I don't actually know, but I think it's fine. So now we can like more precisely sort of drag this along with the super crappy debug system, but you know, it's there. It would be nice to have like, yeah, it would nice to have just like you click, maybe you click the left button, it goes up, and you click the right button, it goes down. Would be like a nicer way to do it, right? Because like, how is that not clamping the value also, right? Like, didn't we select clamping for the value? Why does it not clamp? I guess because this overwrites it. Such a crappy debug system. It's so terrible. Like, I don't know why the clamping is not reflected back in here. Like it's weird. Like, see, that one does, right? But this one doesn't. Why? I mean, no idea. Did I mess up the code that does that? I mean, it sure looks like I'm writing back to it, right? So, you know, why does that not clamp? I have no idea. I do think in this case, maybe I because it's so bad, maybe for now, I actually do have a thing here that's like, you know, instead of drag value, there's like some kind of thing like tick value. So maybe in this case, there's like a tick value. And then when we do that, in here, I would just have one for this that lets you click up or down by one or something crappy like that. You know, I'm not sure exactly what this input state really is, so it's probably easy enough to just say, all right, we've got this exact case here, and it's tick value, and if you see it, you actually just use, like, if the input has, like, you know, the shift key down or something, right? Like something's extremely bad. I don't know why game input cannot be found. It's like right there. But anyway, so if we look here, you've got like shift down or something, so maybe like just shift. If you're pressing shift, it goes upwards. If you're not, you're not, or something, right? So you just say like shift down, you subtract, not down, you increment, and that's it. Although, whoops, that's in the wrong one. This doesn't exist. This does. Yeah, so not great. Again, just because the debug system is super crappy, but I just don't want to deal with it for right now. So we're just going to leave it crappy. And then maybe we can sort of figure out a way to make this do something. Somehow that doesn't seem to actually increment. It will decrement, but it won't increment, which is a little bit weird. Oh, because there's still an if in there. And then that's it. That'll just be what we use. And it's really bad, but oh well. We should have written a better one if we wanted a better one. So there's us sort of going through those particular values, right? I don't know why sometimes it goes too many. I guess if you hold it down, it goes up. Yeah. I kind of only wanted to do on the end of an interaction, so I guess maybe that's this, right? So on end interact, that might be the more, like, sane place to put it. So it could be that, like, this should actually be where that happens. Like right here. So when we do these interactions and like there's the toggle value, like the tick value actually goes in there. And so that you only do it once when you click. It doesn't like keep going while you hold it down. So yeah, that's a lot more sane now. Although it looks like the still looks kind of like that was a little bit weird. Like, why did it stop when we came out? Let's look at this a little closely. So why is 9? Why does only every other one show up? Ah, because I see. Because it's inside the wall area, so it never gets to that point. We should probably include drawing for that, shouldn't we? Yeah. All right, well, anyway. Fair enough. Fair enough. All right, so let's try to set this to something that we actually want to look at. And it's a little bit annoying because we do have sort of light bleed here. I don't know why that doesn't clamp. Like we said before, that's very weird, and I don't understand it. But the debug system is its own painful reality that we will address in good time. So if we look here at the different ways we can cast, we can now kind of step through them. So if we, like, here's one thing. If we step through all the octahedrons, they should each be, like, out a different face. Sorry. If we step through the tx and ty, they should all be out a different face, but the octahedron index should all be out the same face. So basically, like, all of these should be out a downward face of the octahedron. Now, one thing that doesn't make good sense to me is the octahedron isn't aligned this way. So actually, I don't understand why we're getting a straight down arrow for the expected direction, because that's not actually a legal direction for the octahedral map, is it? Like, that doesn't make any sense. How is that a thing? Like, if we look at expected direction, this, how is expected direction for this octahedral map, how is it pointing downward? It should never be able to point downward, should it? I mean, that really just seems wrong. I mean, that's just got to be wrong. So, like, I feel like this routine is busted because there shouldn't. Yeah, I mean, you can just look at how it works, right? When you call direction from tx/ty, you're gonna step in here and you're gonna compute you're gonna remove the apron part of this, right? And you're just gonna step through the oxy coefficient.x is just telling you for each step where are you in the octahedral map, right? So the direction vector heading out of the octahedral map is just going to be based on, I mean, I suppose if you're close to the bottom of the thing, okay, I suppose that's okay. It's not really, because it's not really technically the face of the octahedron that we're looking at here. It's this particular pixel, right? Which could be close to down, sure. I mean, Greg Inc., by the way, no, they're not. Light bleed is kind of a natural thing that happens if you just don't have watertight ray tracing. So, you know, light bleed can mean like, well, I've got a wall and there's a light on the other side of the wall and it comes in, right? And, you know, that's not that big of a problem. You can choose to leave that in if you want. Depends how bad it is or if it affects your gameplay significantly and so on. You know, so that's like light bleed is not that bad. Light poisoning is like when you have some critical error, like we have at least one of at the moment, where some values that are like out of bounds or something cause the entire system to create like basically a feedback loop. It's very much the exact same thing as feedback in audio. So like a microphone and a transmitter are like close to each other and they just go like, you know what I mean? That's happening in the light. And the reason I call it poisoning is because when you have like a radiosity kind of effect, right? If there's any critical bug like that in just one part of your light solution, it will quickly spread to the whole thing because you're bouncing the light around in real global illumination. If you don't do global illumination, you can't really have that kind of light poisoning because your lighting is all local, so it won't spread. But when you have global illumination, your bug will spread. And so that's what I'm talking about when I call it light poisoning. It's not the same as light bleed. Light bleed is something that you might be okay with. Like, it's not necessarily a bug. It is a bug in the grand scheme of things, meaning in terms of the product, but it may not actually be a bug in the lighting system, meaning your lighting system may just not be designed to handle that. So you wouldn't necessarily think of light bleed as like a critical failure. Light poisoning is always a bug. Like it's no matter what you did, you screwed up if you have light poisoning, whereas light bleed might be something you just accept because your lighting algorithm is always approximate, and like you just don't have the, you haven't dedicated the resources to it, or it's too cumbersome or whatever, so light bleed, you're just going to have it in the game and it ships. It's okay, right? So I would like to draw a distinction there, because light bleed is significantly less bad than light poisoning, and what I'm talking about here is actually light poisoning, like the bad, it's the worst case. Light bleed is not nearly as bad of a case. You might still want to get rid of it, but it's not as bad as this. It's not as bad as this situation. Okay, so moving forward, we're doing the grid raycast, and that seems a little bit more sane. I'm okay with that at the moment. Yeah, to a certain extent, right? I don't want to overstate it. So let's suppose we go 1 forward in X to something I can see. So like right here. So that's 10, 4, 1. I'm going to set that to be like what it initializes to at the outset, so that we can, on startup, we're always going to be there. And then I'm just going to like look at some of these casts from here to see what we end up doing for some of the octahedron, right? So there's another cast. These are all should be facing pretty much down. Okay, so there's some really critical failure that's happening when the octahedron index. So supposedly, when we look at the sampling tables that we built, we're supposed to get 16 different octahedron. But from looking at that, we don't. When we get up above a certain number of octahedron, they just look like they're just repeating themselves. And so I don't actually know if that's a problem with the table or a problem with how we're looking up into the table. But it's definitely not correct. You know what I'm saying? So that's the first problem, is we should be able to drive that number all the way to 15, and we shouldn't see it bottom out like that. Now, looking at the table, I would also say that the table itself doesn't look like it has that error, because that error would look like a bunch of things that just have 0, 0, -1 in them or something, right? And that doesn't really seem to be the case, so, And the total number of these that should be in here is 16 times 64. Right? Because total light sample direction count is the octahedrons times the per octahedron. That's 16 times 64. So 16 times 64 is 1024. And I guess I don't know exactly where line 1024 is, but it should still be, yeah. So there's definitely the correct number of vectors in here. So it's not like we're reading off the end of the table or something by asking for those values. So let's take a look and see what's going on here, because something's funny is going on, and I'm not really sure what it is. So in grid raycast, where we're picking out this sample direction, we're starting out the sample table. We're stepping through the octahedrons here, and then through the SY values. The octahedrons, we should be going from 0 to 16 or whatever, right? And did I mess up like this thing? I mean, it still looks correct. So why is that happening? Let me just recompile this real quick so that it has the, oops. What did I do? Accidentally inserted a Z. That's not gonna fly. So that's perplexing, and maybe we just step in debug mode and see what's going on there, but that's pretty wild, and I don't understand it. So the octahedral index, right, we get 0 is right, 1 is right, 2 is right, 3 is right, 4 through 15 are just all wrong. So how is that possible? Like why are all those values apparently just pointing straight down instead of actual correct values? It sure seems like we're stepping too far, or maybe we built the table incorrectly. That's just really, really confusing. And the more I stare at that thing, I can't really figure out exactly why. Maybe we're looking up into that table slightly wrong. Let's take a quick look at. Maybe we're misunderstanding how that table is packed, because it is kind of janky, and we should probably go back and repack it to the way we want it to be packed now instead of trying to pull stuff out of it. But you never know. Let's take a look at that sample direction table stuff, right? So the sample direction table is this thing, I believe. And the walk table offset. Aha. Right. So I kind of see what the problem is here. Yeah. So much like a lot of things here, it's just the fact that we don't work on this code very often, so it falls out of our head. The walk table offset, again, because this is highly optimized code, we don't have the luxury. Well, it's not highly optimized. It is optimized code. We don't have the luxury of having everything be kind of like sparse and easy to modify. The walk table offset is accessed directly from the sample direction table. It probably doesn't line up anymore because previously the walk table offset was generated assuming there were octants and other weird things like that. And none of that may be correct anymore. So we probably need to go make sure that this actually lines up at all, because it might actually just not right now. And we probably have to take this a little more seriously. Right? I mean, that said, this part wouldn't be, though. So maybe that's not really true. Because the ray direction, like ignore walk table temporarily. The ray direction here, that actually should be fine. So now I take it back. Because we would still see it, the direction of the ray should still be correct. So still not quite making sense. So let's try to actually figure out what these values are. I mean, maybe the best thing to do here would be to actually show what this value is. So this, we will actually compute as its own value. We can inspect, and we'll put the directional offset, in there. We will also make it easier on ourselves by doing this. If set debug true kind of a thing. That way I can set a breakpoint on that line, which just speeds things up a little bit instead of having to look at an actual value. So, if we go in there And we look at what sort of numbers we're plucking out of this table. We could also add an assertion that just says, look, let's make sure we're not outside the table. When we get here, let's just look. Like, so what are all these values? So what's dir offset, for example? Right? Okay. And so now if I change like solution, so let's go change the debug pick octahedron. I don't know if I can edit these. Maybe I can. Let's change this to something that was previously bad. So 10, right? So now let's see what the directional offset is now that it's 10. So that seems fine, right? I mean, that doesn't seem weird. And what's ray d single at this point? I mean, how is it getting that value? So sample dir plus dir offset is the sample direction table. So solution sample direction table, right? Here's the table. We are looking at this 640th one of those. And you're telling me that that's the zero, then that appears nowhere in that table. Like, those values are not in the table. So this lookup is broken. We were correct before when we were like, this looks suspicious, but somehow our suspicions failed to actually find the problem. Because there is a problem, but I don't know what it actually is. One question would be, do we copy this table? And if the answer is that we copy the table, are we copying it wrong? I don't know. So maybe let's take a little bit closer look at that. But in general, so sample dir now is actually indexing into what we think would be a correct placement of the table. There's 1,024 entries in it, and we're only on entry 640. We should be pulling off an actual valid entry of the table. If we look at light sample direction here, right, like we should have, this should have been in the right place. So I don't know. I'm going to try one other thing. I'm going to look at sample direction table directly. So the global variable, sample direction table, right? This is the actual table. That's the hard-coded table before it gets copied into the lighting system, if that's what actually happens. If I go to number 640, am I going to see straight downward pointing vectors there? I don't know. There's only 512 of them. And what is this about? Are those actually there? I don't remember seeing that. If I go to 512, which would just be slightly down from here, I don't see those values. Maybe I do. Oh, well, no, I do. That's one. How many of those are there? So here's the scary part. Looking more closely at the table, they're in there. So it looks like the culprit actually here is our table build. Like, our table is actually busted. For reals, though. For reals. So that's oh no Sunday, it's 3-dimensional global illumination at the moment. Although we could simplify it down to being more 2D. At the moment it's like completely 3D, but we may not really need it to be that. Although it seems fast enough, so we'll probably just leave it as 3D. But we could simplify it further and make it like really just 2D, because the world is pretty 2D. So you could do you could take more advantage of that. At the moment, it's the only thing that we really did there is we just squished it down so we're only computing a very small number of light probes, because since the world is 2D, we don't need a lot of probes in Z, right? So we get a speed boost from the fact that the world is not very large in Z, but at the moment we really don't take advantage of it any other way. So we could eventually move to something that takes more advantage of the 2D nature of things, but at the moment we don't really. You know what I mean? Anyway. Well, that's good to know. So I guess the answer is the table generator is now needs to get fixed before we do anything else, because we can't really count on what we're looking at with the table. So, so that kind of has to get fixed. I don't actually even remember where we had that. It's not in the light profiler. It's H8 sphere, right? So in H8 sphere, we go through and we generate these distributions, and the place where those kind of null, like those BS distributions, I believe are probably coming from like this. So if we don't find something on the sphere that can go out that can go in the direction we're trying to go for this particular one, I think that's probably what's happening there. So yeah, like, hard to say. Probably what we want to do here is just switch to stratified sampling. We can probably fix this to be a little bit better than it is anyway. But I think that's what we actually need to do here. So this code probably needs to be cleaned up pretty much as the next thing to do. And then we can finish debugging the raycasting, which now I'm wondering, how much this has been contributing to our lighting woes, right? So fixing this table, maybe we should save that till next weekend, because we know that's starting in fresh. So I think we kind of know what we have to do. So maybe we save that till the next time. We fix the table, and we can, while we're doing that, we reorganize the table so that it just samples in the correct order, so that this garbage goes away, right? Because now we don't have to use a table that was built for the old system. We just build the table in the correct order. When we build the table in the correct order, we will solve, and we'll fix what was happening here, where we weren't, we're obviously generating totally bogus samples. So we'll generate the table that way, and we can then, I think, just at that point, I think we just go ahead with debugging the raycasting then, because that should eliminate the problem we're seeing currently. And I don't know how much of our problems that we're seeing have to do with the table being bad, because that may have caused other problems as well. We don't know how much bad stuff there is in this table. It's also possible that the sample directions now could just be randomized samples that are stratified inside each of the different octahedral regions. And that may actually be preferable now. So instead of doing Poisson sampling, which is what we were doing before, it may make more sense now to switch to basically stratified sampling, where we just say, let's pick white noise inside the XY, the TXTY locations. It's probably still better to do Poisson distributions. I mean, It's probably still better. Because, okay, you're not allowed to comment on that if your name is literally Poisson process on Twitch. Poisson distributions are still going to be better. So we probably just want to fix the sphere distribution. It's a little bit hard because when you produce a Poisson distribution over the sphere, you then have this problem of you're going to have to be at least slightly oversampling because otherwise you won't get enough samples falling within each one of your grid locations, each one of your octahedral quadrants, right? So you kind of have this problem where you have to sort of set your coefficients conservatively so that you have a Poisson distribution, but the Poisson distribution is slightly more dense than what you're actually going to use, so that when you go to pick elements out of it, you always know that you'll have enough in each one of your regions, right? And we could make the generator sort of aware of that. So one thing the generator could do is it could sort of say, well, look, we're going to keep increasing the density of the Poisson distribution until we get one where there's the right number, that seems plausible. So yeah. Sorry, what's the question there? Will it still be mapped to the octahedral map? Because if so, couldn't we just generate the noise on there that is a square surface, right? So the problem with that is that we want to sample the sphere evenly. You know what I'm saying? We don't care about sampling the octahedral map evenly, because the noise in our lighting is going to come from sampling the sphere evenly or unevenly. The fact that they have to then get bucketed into texels on the octahedral map is kind of incidental, right? So we just want to make sure that we have 16 in each one, but we want them to be evenly distributed on the sphere, not on the octahedron. We don't care how they're distributed on the octahedron at all, except that there needs to be 16 of them per tile, right? So I don't know that we really want to generate them on the octahedron. I mean, you could generate the octahedron, but you still want to measure, as far as the Poisson nature of the distribution, you want to measure it on the sphere, not on the octahedron, unless I'm missing something there, if that makes sense. So I'm going to say I think we're in good shape here. This is looking pretty good. I think we just need to then say, all right, we're going to do the next stream. We start off, the first thing we do is rebuild the tables, and we make sure the tables are really good, right? So that's our next goal. And while we're doing that, we can nicely rearrange them so that we step through the table linearly here, right? And I think you could also, so the other nice thing about this is we can change this to a single loop. So what we can do next time, right, is you can replace this loop with something that looks like this. Or like, so imagine it looks something more like this. You know? So now, because the only reason we needed this internal loop in the first place is because we need transfer PPS to write out correctly as a row. But we don't actually need to do 2 loops. We just need to make sure that we're writing into the right slot of this. So we can just then change it to us just streaming through all of these values and picking out the correct ray. You know what I'm saying? So the other thing we can do now is change the table to just be like, we literally just walk through this entire table doing this each time. And in fact, we can't even do something, we can even do better than that. We can have it so that we don't pass sy anymore. What we can do instead is just have it so that this function here, we can just have it so that this actually executes on the outside of the sy loop. Like we just change this so that instead of the octahedron being here, the sy loop is actually here, and then we change this because we don't really need it. So we can weld all of this together now, right? I don't think there's any way to really do anything fancier than that, but yeah. But I think that's everything, right? So I do think next time we've got a pretty clear set of things. We know exactly what we want to do. So I think that's fine. And so I think we'll call it here. And then we'll go next time and just look at building the table correctly. So it's just one stream. You do the stream straight through, and yeah, and then and off you go. In fact, you could just do this. And only advance transfer PPS each time. I'm not sure. So one thing that is just sort of a bigger question here is, now that we know we're going to do this entire like raycast convolution thing here, where we do the entire set of rays all at once, it may also be the case that there's just a smarter way to batch them than this. And that I don't know. So we'll have to think about that as well. But for now, I'm going to leave it there, and we will come back to this next time. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. I will be back here next time to regenerate that table, and then I think we will be in better shape. All right. Take it easy, everybody. I'll see you next time.